There's something deeply humbling about staring up at a clear night sky, millions of stars scattered across the darkness, each one a sun, many with planets of their own, and all of it so impossibly far away that the light we see began its journey long before humans even walked the earth. In that vast, quiet expanse, it's easy to feel small, isolated, adrift in a universe that seems mostly empty and silent. But what if it isn't? What if, hidden within that cosmic quiet, there are messages, whispers from the void that we're only just beginning to hear? For decades, astronomers have been tuning into the universe, listening for anything out of the ordinary, and what they've found is both thrilling and deeply mysterious. Strange, powerful signals that pulse through the darkness, sometimes repeating, sometimes vanishing without a trace, all hinting at phenomena we don't yet understand. Today, we're diving into one of the most compelling mysteries in modern astronomy, the enigma of unexplained galactic signals. These aren't just random blips or interference. They're structured, energetic, and they defy easy explanation. Some arrive with the power of hundreds of millions of suns, lasting just milliseconds. Others repeat in patterns that tease us with the possibility of intelligence behind them. Each one is a cosmic puzzle, a piece of a story we're still trying to read. And behind each signal lies a web of theories, some grounded in the laws of physics as we know them, others venturing into the extraordinary. Could they be the echoes of collapsing stars, the signatures of unknown celestial objects, or something even more astonishing? In this video, we'll explore 30 of these unexplained signals and the fascinating ideas scientists have proposed to make sense of them. This isn't just a list, it's a journey to the edge of what we know, a chance to peer into the depths of space and wonder at its secrets. Whether you're a long-time space enthusiast or just curious about the universe's greatest mysteries, there's something here to capture your imagination. So settle in, look up, and let's explore the signals that remind us the cosmos is far from silent. It all began with a single, powerful burst of radio noise that would become the stuff of astronomical legend. On a quiet August evening in 1977, the Big Ear radio telescope at Ohio State University was performing its usual, methodical scan of the heavens, listening for anything out of the ordinary. This was part of the long-running search for extraterrestrial intelligence, or SETI, project, a patient effort to find a needle in the cosmic haystack. For the most part, the data it collected was a steady hum of cosmic static, the background noise of the universe. But that night, something extraordinary happened. The telescope's system recorded a signal so strong, so seemingly artificial, that it defied all conventional explanation. It wasn't a gradual rise in activity. It was a sudden, intense spike that came out of nowhere and vanished just as quickly, lasting for a full 72 seconds. The exact amount of time the Big Ear could focus on a single point in the sky. The real magic and the source of its enduring mystery lies in the signal's specific frequency, 1420 MHz. This isn't just a random number on the dial. In astronomy, this is known as the hydrogen line, a frequency that hydrogen atoms naturally emit in the void of space. Scientists like Philip Morrison and Giuseppe had theorized years earlier that this would be a logical, universal watering hole for any advanced civilization trying to announce its presence. The idea was that any species with a basic understanding of physics would recognize this frequency as a natural, quiet channel in the radio spectrum, a clear place to shout into the darkness without cosmic interference. So when the Big Ear detected a signal precisely at this frequency, it wasn't just unusual, it was almost exactly what they had been hoping to find. A few days later, astronomer Jerry Amon was reviewing the computer printout of that night's data, a long list of alphanumeric characters representing signal strength. As his eyes scanned the page, one particular sequence jumped out at him. 6 characters 6EQUJ5, indicating a signal intensity so far off the charts that it was virtually unprecedented. In that moment of stunned realization, Eamon grabbed a red pen, circled the sequence, and simply wrote "Wow" in the margin. That single word of astonished annotation gave the signal its famous name and captured the sheer disbelief and excitement of the discovery. It felt in that one moment like we might have finally heard something. Yet the story of the WOW signal is defined more by its absence than its presence. Despite decades of relentless searching by telescopes around the world, and even dedicated efforts aimed directly at the same patch of sky in the constellation Sagittarius, the signal has never been heard again. It was a one-time event, a cosmic scream that fell silent. This utter lack of repetition is what has fueled both its legendary status and the endless debate over its origin. The most likely natural explanations, like a comet passing through that region of space, have been proposed and largely debunked. Comets have their own broad emissions and wouldn't produce such a sharp, focused signal on that specific frequency. Without any repeat performance, the signal remains frozen in time, a perfect, unsolved mystery. It stands as a tantalizing piece of evidence that we might not be alone, and a frustrating reminder of just how vast and silent the universe truly is. It was the first great modern mystery from the cosmos, and it set the stage for everything that followed. Just when the scientific community thought it had the WOW signal neatly filed away as a glorious, one-off anomaly, the universe delivered another surprise that would upend everything we thought we knew about these cosmic shouts. For years, the handful of similar powerful bursts that were discovered were all singular events, brief, brilliant explosions of radio energy that flashed once and were never seen again. This pattern firmly supported the leading theory that they were the final, catastrophic death cries of massive celestial objects. Imagine a star collapsing into a black hole or two incredibly dense neutron stars merging in a violent collision. Such an event would release a titanic amount of energy in one magnificent, irreversible pulse. That model was clean, elegant, and satisfying, but the cosmos, it seems, has a preference for chaos over order. In 2012, at the legendary Arecibo Observatory in Puerto Rico, a colossal dish nestled in a natural limestone sinkhole, astronomers were engaged in a routine survey of pulsars. These spinning neutron stars are the universe's timekeepers, emitting regular radio pulses with metronomic precision. But amid this predictable rhythm, the team detected something that shouldn't have been there, an extremely intense burst of radio waves that lasted just a few milliseconds. Initially, it was catalogued as just another fast radio burst, a phenomenon so new it still carried an air of mystery. They designated it FRB 1212, named for the date of its discovery, November 2nd. It was intriguing, but it fit the established pattern of a single, cataclysmic event. The assumption was that whatever created it had been destroyed in the process. Then in 2015, something extraordinary happened. The same team, using the same powerful telescope, pointed back at the same coordinates. And there it was again, not just once but multiple times. The source was repeating. This wasn't the signature of a one-time explosion. This was a persistent object, something that could survive its own immense outbursts and do it again and again. The discovery sent shockwaves through the field of astronomy. It was as if a bomb had gone off, only to reassemble itself and explode again moments later. This simple observation completely dismantled the leading cataclysm theory. You can't have a star die multiple times in the same spot. This was something entirely new, something that could endure. Pinpointing the home of this repeater became an urgent astronomical quest. Using a network of the world's most powerful telescopes, researchers eventually traced the faint, lingering glow of its source to a startlingly unexpected environment. A tiny, faint dwarf galaxy more than 3 billion light-years from Earth. This was another crucial piece of the puzzle. This wasn't a large, mature galaxy like our Milky Way, bustling with stars. It was a small, primitive galaxy, actively forming new stars. This environment suggested that whatever was producing these incredibly powerful signals might be linked to the raw, energetic processes of star birth rather than star death. The source of the bursts was located in a region of this galaxy that was brimming with ionized gas and energetic activity, a cosmic nursery where extreme physics is the norm. The repeating pattern itself added another layer of profundity to the mystery. The bursts weren't just random, they arrived in clusters. There would be periods of frantic activity, with multiple bursts happening in quick succession, followed by long stretches of utter silence. This cyclic behavior pointed to a source that was somehow periodic, perhaps orbiting another object that periodically triggered its outbursts, or something with a rotational or precessional cycle that only occasionally aimed its beam of radio energy in our direction. This wasn't just a repeating signal, it was a repeating signal with a personality, a rhythm that hinted at underlying mechanics we are only beginning to grasp. FRB 1212 forced a great and humbling intellectual reckoning. It proved that our universe harbors phenomena that are not only powerful but also persistent, and that our theories must expand to accommodate a reality far stranger and more wonderful than we had previously imagined. If the discovery of a repeating fast radio burst was a shock to the system, the next one to be uncovered was nothing short of a revolution. It presented a characteristic so strange, so unnervingly precise, that it felt less like a natural cosmic event and more like a piece of machinery ticking away in the void. This is the story of FRB 180916, a signal that doesn't just repeat, but does so with a clockwork rhythm that has profound implications for every theory we have. Its story begins with a new eye on the cosmos, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike the massive, single-dish design of Arecibo, CHIME is a radically different kind of instrument, a stationary array of 4 half-cylinders that acts like a cosmic fish-eye lens, scanning the entire northern sky every single day. This immense field of view makes it a perfect hunter for transient events like fast radio bursts, and it was this powerful new tool that detected the bizarre pattern emanating from a distant spiral galaxy. What CHIME found was unprecedented. The bursts from this source were not random, nor did they arrive in chaotic clusters. Instead, they followed a perfect, predictable 16-day cycle. For approximately 4 days, the source would actively fire off bursts, sometimes several in an hour, sometimes just one. Then, as if a cosmic switch was flipped, it would fall completely silent for the next 12 days. After this period of quiet, the cycle would begin anew with absolute regularity. This wasn't just repetition, this was periodicity. It was a cadence, a rhythm written into the fabric of the signal itself. This precise 16.35-day cycle immediately ruled out entire categories of one-time cataclysmic events. You simply cannot have a stellar explosion on a schedule. This pointed overwhelmingly to a source that was periodic by its very nature, an object whose environment or internal mechanics was governed by a clock. The location of this cosmic metronome added another critical layer to the puzzle. Precise measurements pinpointed its home not in a faint dwarf galaxy, but within a star-forming region of a sprawling spiral galaxy some 500 million light-years from Earth. This places it significantly closer to us than the host of the first repeater, making it a far brighter and clearer laboratory for study. The fact that it resides in a familiar spiral galaxy like our own Milky Way suggests that whatever engine is powering these bursts is not exclusive to rare or primitive galactic environments. It might be a phenomenon that is relatively common, happening in the stellar nurseries of galaxies across the universe, which is both a comforting and a daunting thought. So, what kind of natural object could possibly behave this way? Astrophysicists have raced to develop models that can explain this 16-day on and off pattern, and the leading theories are as fascinating as they are complex. One compelling idea involves an orbiting system. Imagine a highly magnetized neutron star, a magnetar, in a wide, eccentric orbit around another massive star. The intense gravitational and magnetic fields near the companion star could periodically trigger eruptions on the magnetar's surface as it swings through its closest approach, a 4-day period of violent activity. As it travels to the far, cooler part of its orbit, the activity would cease, creating the 12 days of silence. This binary model elegantly explains the clockwork nature through fundamental orbital mechanics. Another possibility involves the concept of precession. A neutron star spinning at incredible speeds doesn't always spin on a perfectly stable axis. It can wobble, much like a spinning top slowing down. This wobble is called precession. If the beam of radio waves is shooting out from a particular spot on this wobbling star, it would only point directly at Earth for a specific window during its precession cycle, neatly accounting for the active window before swinging away and leaving us in radio silence for the rest of its cycle. This model requires no companion star, placing the entire incredible mechanism within a single, albeit wildly energetic, object. And then, of course, the precise regularity inevitably sparks more speculative ideas. Could such a perfect rhythm be the product of an artificial structure? The concept of a beacon, a deliberately timed transmitter sweeping the galaxy, is a trope of science fiction that finds a curious echo in this very real signal. While extraterrestrial intelligence remains the explanation of last resort, the sheer mathematical precision of FRB 1809-16 forces us to acknowledge that the universe is capable of creating natural clocks that rival our best human-made timepieces in their regularity. It stands as a testament to the fact that the cosmos is filled with rhythms and cycles we are only beginning to hear, each one a new verse in the symphony of the stars. While the discovery of repeating fast radio bursts opened up a new chapter in cosmic mysteries, another signal from the early days of the search for extraterrestrial intelligence continues to intrigue scientists for a completely different set of reasons. This is the story of SHB-02+14a, a signal that didn't arrive with the explosive power of an FRB, but instead whispered onto the scene through the collective effort of millions of home computers around the world. This was the flagship discovery of SETI at home, a groundbreaking project that harnessed the unused processing power of volunteers' personal computers to analyze vast amounts of radio telescope data. It was the ultimate citizen science experiment, and in 2003, it seemed to have found its first great prize. The signal's most compelling feature was its frequency, a detail that immediately caught the attention of every SETI researcher. SHB-02+14 was broadcasting at exactly 1420 MHz, the universal watermark of hydrogen. Just like the WOW signal decades before it, this wasn't a random choice. Hydrogen is the most abundant element in the universe, and its resonant frequency is considered a fundamental channel, a logical place for any advanced civilization to transmit a beacon. Finding a signal here was like hearing a clear voice calling out on a known, open channel. It felt intentional, designed to be found. But the plot thickened with the signal's bizarre behavior, a characteristic known as Doppler drift. As a transmitter on a rapidly rotating planet moves toward and then away from us due to its spin, its signal will subtly shift in frequency, much like the pitch of a siren changes as an ambulance races past. This signal exhibited a very specific amount of drift, one that closely matched what you would expect from a transmitter located on a planet orbiting a distant star, a planet with a rotation similar to that of Earth. It wasn't just a steady tone, it was a tone that was changing in a way that suggested it was anchored to a spinning world, a detail that felt almost too perfect to be natural. The source of this enigmatic transmission only added to its mystique. The coordinates pointed to a seemingly empty patch of sky near the border between the constellations Pisces and Aries. This region is not known for any prominent stars, certainly none with confirmed planetary systems that could host a potential source. It was, by all accounts, a cosmic dead zone, which made the presence of a strong, drifting signal even more puzzling. Was it coming from a star so distant we couldn't see it, or was its origin something even more exotic? Despite its incredibly promising characteristics, SETI-02 plus 14 has never been confirmed. The signal was detected not once, but on 3 separate occasions, each time from the same location. However, it was incredibly weak and frustratingly brief, and perhaps most damningly, it was never detected by any other radio telescope. This has led many scientists to conclude it was likely a product of terrestrial interference, a random combination of noise that just happened to mimic the exact signature everyone was hoping to find. It could have been a glitch in the software, a quirk of the complex data processing, or even a faint signal from a passing satellite that slipped through the filters. Yet it has never been entirely explained away. The specific combination of the hydrogen line frequency and the precise Doppler drift makes it a statistical outlier, a 1 in a million fluke if it was merely random noise. It remains a tantalizing what-if in the annals of SETI, a signal that had all the right ingredients to be the one we were waiting for, but which vanished before its true nature could be proven. It stands as a monument to both the incredible promise and immense challenge of the search, a ghost in the machine that continues to whisper from the void, forever on the edge of discovery and doubt. While the WOW signal captured the public's imagination and the repeaters rewrote the rulebook, the entire field of fast radio burst science owes its existence to a single, forgotten blip in an old data archive. This is the story of the Lorimer burst, the original FRB, a discovery so monumental that it was initially met with profound skepticism. The year was 2007, and astronomer Duncan Lorimer was not actively searching for mysterious cosmic signals. Instead, he was supervising a student project, sifting through old observational data from the Parkes Radio Telescope in Australia. The data itself was from a survey of the Magellanic Clouds conducted 6 years earlier in 2001 and was largely considered to have been thoroughly mined for all its useful information. It was the astronomical equivalent of finding a priceless painting in a dusty attic. What Lorimer and his student found was anything but ordinary. Hidden in the reams of numbers was a single, spectacular spike of radio energy that defied all categorization. It was unimaginably bright, a 5-millisecond burst so powerful that it outshone the entire rest of the universe in that radio frequency for its brief moment. But its true significance was revealed by a specific characteristic known as its dispersion measure. As radio waves travel across the vast distances of intergalactic space, they pass through clouds of free electrons. These electrons act like a subtle cosmic prism, causing lower frequency waves to travel slightly slower than higher frequency ones. The result is that a short, sharp signal gets dispersed, arriving at our telescopes as a descending whistle. The greater the spread or dispersion, the more material the signal has traveled through, and thus the farther it has come. The dispersion measure of this burst was off the charts. It was far too high to have originated from anywhere within our own galaxy. The inescapable conclusion was that this millisecond flash had come from an utterly colossal distance, far beyond the Milky Way. The energy required to produce a signal that bright from that far away was staggering. In that tiny fraction of a second, the source had released as much energy as the sun puts out over 80 years. The idea that a natural cosmic event could be so brief yet so unimaginably powerful was at the time almost heretical. The physics simply didn't seem to allow for it. Unsurprisingly, the astronomical community greeted the discovery with deep skepticism. The initial assumption was that it had to be some form of local interference, a glitch from a passing satellite, a piece of Earth-based electronics, or even an artifact from the telescope itself. The fact that it was a lone event, never seen before or since in that dataset, made it easy to dismiss as a one-off anomaly. For years, the Lorimer burst remained a controversial outlier, a celestial unicorn that most scientists felt was more likely to be a problem with the data than a true revelation about the universe. It took the subsequent, independent discovery of more of these bursts by other telescopes around the world to finally vindicate Lorimer's finding. His perseverance in the face of doubt had uncovered an entirely new class of astronomical phenomenon, one that would eventually force us to confront the most energetic and mysterious processes in the cosmos. The Lorimer burst was the first glimpse of a hidden universe, a universe capable of violence on a scale we are still struggling to comprehend. Of all the places in the cosmos from which we might hope to receive a signal, the very closest star system to our own would be the most astonishing, the most paradigm-shattering of all. In late 2020, it seemed for a brief, electrifying moment that this exact scenario might be playing out. The star in question was Proxima Centauri, a red dwarf just over 4 light-years away, and home to at least one confirmed rocky planet, Proxima b, orbiting within its habitable zone. The discovery was made by the Breakthrough Listen project, one of the most ambitious and well-funded SETI initiatives in history, using the 64-meter Parkes radio telescope in Australia. They weren't even specifically targeting Proxima Centauri at the time. The star was simply in the field of view while the telescope was studying a flare from the star itself. It was during this routine observation that the system flagged something extraordinary. A pristine, narrowband signal they designated BLC1. The characteristics of this signal were precisely what SETI scientists had been hoping to find for decades. First and foremost, it was a narrowband transmission. In nature, radio emissions are almost always broadband, splashed across a wide range of frequencies. Think of the static hiss between radio stations. BLC1, by contrast, was a laser-like beam focused on a single, specific frequency. This is a hallmark of technology, a way to pump a lot of energy into a tight channel to make it propagate clearly across vast distances, exactly the kind of signature an artificial transmitter would create. Furthermore, the signal exhibited Doppler drift, a subtle shift in its frequency over time. This is the telltale sign of a transmitter on a moving platform, like a planet rotating on its axis, which would cause the signal to compress and stretch relative to our vantage point on Earth. It was as if the signal was checking every box on the list of what an authentic alien broadcast should look like. The specific frequency it occupied only added to the initial intrigue. BLC1 was detected at 982 MHz, a band that is notably quiet in nature, free from the background chorus of cosmic emissions. However, this is also a frequency heavily used by human technology, specifically by satellites and aircraft. This dual nature, perfect for interstellar communication but also hopelessly terrestrial, immediately placed the signal in a gray area. The excitement within the Breakthrough Listen team was palpable but guarded. They knew all too well that the history of SETI is littered with signals that ultimately pointed back to our own technology. A year-long, painstaking investigation followed, an exhaustive process of elimination that is a masterclass in scientific rigor. The team scoured every possible angle. They looked for other telescopes that might have been observing the same patch of sky at the same time, which could have caused cross-interference. They examined the signal's behavior in minute detail. A key piece of evidence emerged when the Parkes telescope moved off target, pointed away from Proxima Centauri. The signal disappeared, but when it swung back, the signal reappeared. This on-off phenomenon is a classic test for a genuine celestial source, as human interference typically bleeds into the telescope's receivers regardless of where it's pointing. This single observation was perhaps the most compelling reason to believe BLC1 might be real. Yet, the ultimate conclusion was a disappointment, though a fascinating one. After ruling out every known natural astrophysical source, the team determined that BLC-1 was almost certainly human-generated radio frequency interference. The most likely culprit was a form of intermodulation distortion, a phenomenon where two or more strong radio signals from human sources, perhaps a nearby radio tower and a passing satellite, mixed together inside the slightly non-linear electronics of the telescope itself, creating a spurious third signal at a completely new frequency. In this case, that phantom signal just happened to appear at 982 MHz and just happened to drift in a way that mimicked a transmitter on a distant exoplanet. It was a cosmic prank played by the universe's most common joker, ourselves. Despite this definitive attribution, BLC-1 remains a landmark event. It wasn't a false alarm in the traditional sense. It was a precisely identified case of extremely sophisticated interference that perfectly mimicked an anticipated technosignature. It taught the SETI community an invaluable lesson. Our own technology is becoming so pervasive and complex that it can generate false positives more convincing than any natural cosmic phenomenon ever could. It forced a refinement of detection and verification protocols, making the entire search sharper and more resilient. BLC-1 is the ghost we had to learn to see through, a reminder that the greatest obstacle to finding a signal from another world might be filtering out the ever-growing noise of our own. Imagine a star almost a twin of our own sun, a yellow dwarf sitting 95 light-years away in the constellation Hercules. Around it orbits at least one known planet, a Neptune-sized world. It's a system that, on the surface, seems comfortingly familiar, but in 2015, this star, known as HD 164595, did something utterly extraordinary. It appeared to shout our name. The detection was made by the Russian Academy of Sciences Rattan 600 radio telescope, a unique instrument composed of a giant ring of rectangular panels. While engaged in a routine survey, the telescope recorded a powerful, singular signal from the direction of this sun-like star. It wasn't a dispersed cosmic whistle or a random burst of static. It was a strong, narrowband signal, the kind that technology produces. The frequency of this transmission sent a jolt through the small community of astronomers who learned of it. It was detected at 11 GHz, a wavelength that falls within what is often called the water hole, a relatively quiet band of the radio spectrum that scientists have long speculated would be ideal for interstellar communication. But the real shock came when researchers calculated the potential power behind such a signal if it truly was a deliberate broadcast aimed into the galaxy. The numbers were staggering. For the signal to be an omnidirectional broadcast, like a television tower blasting energy in all directions, the power required would have been on a scale we can barely fathom, equivalent to the total energy output of a civilization that had harnessed the entire power of its star. This is the very definition of a Kardashev Type II civilization, a concept that had lived only in the realms of theory and science fiction until that moment. The idea was so profound it forced a reconsideration of what might be possible. If the signal was not a general broadcast but a tightly focused beam deliberately aimed at our solar system, the power requirements dropped dramatically to a level within the conceivable range of our own future technology. This opened up two equally mind-bending possibilities. Either we had stumbled upon a civilization so advanced it built structures around its sun, or we were the intended recipients of a targeted message from a society not too far ahead of our own. The implications of either scenario were nothing short of revolutionary. Yet, as with so many of these stories, the initial excitement was met with the sobering wall of silence. The international astronomical community immediately swung into action, training some of the world's most powerful listening posts, like the Green Bank Telescope in West Virginia and the Allen Telescope Array in California, back at HD 164595. They listened intently, scanning the same frequencies for any hint of a repeat performance. They heard nothing. The star had gone quiet. The signal, dubbed by some as a potential wow signal 2.0, never returned. This lack of repetition is the heart of the mystery and the source of continued debate. Without a second act, the signal remains an enigma, a single data point in a sea of noise. The most probable explanation, and the one favored by many scientists, is that it was a fleeting case of terrestrial interference. The 11 GHz frequency is used by military and communication satellites, and it's entirely possible that a secret satellite transmission or a bounce from a piece of space debris was misinterpreted by the telescope's unique ring-like design. However, the Russian team maintained that the signal's characteristics and the way it tracked with the star's movement across the sky made a terrestrial source less likely. This division highlights the immense challenge of this work, distinguishing a cosmic whisper from the ever-growing cacophony of our own technological noise. The signal from HD 164595 remains a compelling might have been, a tantalizing glimpse of a possibility that vanished before it could be proven, leaving us to wonder if for one brief moment we truly heard a call from a star not so different from our own. Just when we thought the fast radio burst phenomenon couldn't get any stranger, the universe delivered a holiday surprise that would stretch our definitions to the breaking point. On December 25, 2010, as much of the world celebrated Christmas, the giant Arecibo radio telescope in Puerto Rico was doing what it always did, listening to the cosmos. Amid the usual data stream came something that made astronomers do a double take, a radio burst that refused to play by the established rules. While typical FRBs are incredibly brief, lasting mere milliseconds, this event continued for a breathtaking 30 minutes, an eternity in the world of cosmic transience. This wasn't a quick shout into the void, it was an extended monologue, and it immediately earned the memorable nickname, the Christmas Burst. The extraordinary duration of this event placed it in a category all its own. Normal fast radio bursts release their incredible energy in a flash so brief that it challenges our instruments to capture all the details. The Christmas burst, officially catalogued as FRB 101225, completely overturned this expectation. Its prolonged emission suggested an entirely different physical process was at work, one that could sustain energy release over minutes rather than milliseconds. This wasn't the signature of a catastrophic one-time collapse or collision. It pointed towards something that could continue producing energy, something with staying power that existing models couldn't easily explain. Scientists scrambled to find explanations for this anomalous event, and two particularly compelling theories emerged from the debate. The first involved a special type of neutron star known as a magnetar. These incredibly dense, rapidly spinning stellar corpses possess the most powerful magnetic fields in the universe, trillions of times stronger than Earth. Occasionally, these magnetic fields can become twisted and unstable, leading to massive starquakes on the neutron star's surface. These seismic events can trigger enormous flares of radiation. The Christmas burst's extended duration could potentially be explained by a series of such flares occurring in rapid succession, like cosmic aftershocks following a major stellar tremor, creating a prolonged period of emission rather than a single brief flash. The second theory ventured into even more exotic territory. What if a rocky body, perhaps a large asteroid or even a small planet, collided with a neutron star? The mechanics of such an event are almost beyond imagination. As the asteroid approached the neutron star, it would be torn apart by unimaginable tidal forces, shredded into a stream of debris. This material would then rain down onto the star's surface at nearly the speed of light, creating a continuous series of impacts across the star's surface. Each impact would release a tremendous amount of energy as the material was instantly vaporized upon contact with the ultra-dense surface. This could create a sustained eruption lasting for many minutes, perfectly matching the observed duration of the Christmas burst. It's a scenario that combines the destructive power of a collision with the enduring energy release of a prolonged event. What makes the Christmas burst particularly frustrating for astronomers is that it remains a singular event. Unlike the repeating FRBs that have been studied extensively, this 30-minute marvel has never been observed again. Without additional examples to study, researchers cannot perform the comparative analysis needed to distinguish between competing theories. Is it part of a known class of objects that simply exhibited extreme behavior this one time, or does it represent something entirely new? The lack of repetition means we have only this single data point, a unique fingerprint that doesn't match any others in our growing cosmic database. This enduring mystery highlights an important truth about astronomical discovery. Sometimes the most valuable findings are the ones that don't fit neatly into our existing categories. The Christmas burst continues to challenge astrophysicists to expand their models of high-energy transients, forcing consideration of mechanisms that can operate on vastly different timescales than previously thought possible. It serves as a reminder that for every rule we establish about the universe, there exists an exception waiting to be discovered. A cosmic gift that keeps on giving to scientific inquiry long after the holiday decorations have been put away. Sometimes the hunt for cosmic messages doesn't begin with a single, startling event, but with a slow, creeping pattern emerging from a mountain of data. This is precisely what happened with a study that sent a ripple through the astronomical community in 2015. A claim so extraordinary it was met with immediate and intense skepticism. A team of astronomers from Laval University in Canada was conducting a meticulous analysis of over 2.5 million stars catalogued by the Sloan Digital Sky Survey. They weren't searching for aliens, they were engaged in the painstaking work of classifying stellar spectra, the unique fingerprints of light that reveal a star's chemical composition. Their method was purely statistical, using algorithms to sift through this colossal dataset and flag any stars whose light patterns exhibited unusual, non-random features that defied easy classification. What the algorithm identified was astonishingly specific. Out of those millions of stars, it pinpointed exactly 234 stars that appeared to be emitting peculiar pulsed signals. The pattern was eerily consistent. These stars, all remarkably similar to our own Sun in their spectral type, were producing tiny, rapid dips in their light output. These dips weren't random, they seemed to be periodic, occurring in regular pulses spaced at intervals that suggested an intelligent, artificial origin. The Laval team, led by Professor Ermanno Bora, put forward a hypothesis that was as breathtaking as it was bold. They proposed that these precise, synchronized pulses could be evidence of extraterrestrial laser communication. The idea was that an advanced civilization might be using powerful lasers to send brief, directed pulses of light across the galaxy, perhaps as a beacon. As this laser light momentarily outshone the star's own natural emission, it would create the exact kind of subtle, periodic dip in the spectrum that their algorithm had detected. The scientific community's response was swift and overwhelmingly skeptical. While the idea of a galactic internet made of light was captivating, astronomers quickly pointed out that extraordinary claims require extraordinary evidence, and this finding was riddled with potential pitfalls. The primary criticism focused on the statistical method itself. When you analyze a dataset of millions of objects, you are almost guaranteed to find some number of apparent patterns purely by random chance. Finding 234 stars exhibiting a similar anomaly was intriguing, but without a clear physical mechanism or any independent verification, it was far more likely to be a statistical fluke, a classic case of p-hacking, where you can find a seemingly significant result in any large enough dataset if you look hard enough and don't account for all the variables. The most probable explanation, championed by skeptics, involved the stars themselves. Many of the flagged stars are known to be chemically peculiar, belonging to a class called Lambda Boötis stars. These stars have unusual abundances of certain elements in their atmospheres, which can cause complex and sometimes poorly understood variations in their spectral lines. Pulsations within the stars themselves, or even instrumental effects from the telescope and spectrograph used to collect the data, could easily mimic the kind of periodic dips the team reported. The Allen Telescope Array, a facility dedicated to the search for extraterrestrial intelligence, subsequently trained its dishes on a subset of these stars and found absolutely no evidence of the pulsed signals in question, dealing a significant blow to the alien laser hypothesis. In the end, the consensus within astronomy is that the 234 signals are almost certainly not messages from alien civilizations. They are a fascinating example of how a powerful pattern recognition tool can uncover anomalies, but they also serve as a critical lesson in scientific caution. The universe is full of natural phenomena we have yet to fully understand, and it is always more prudent to exhaust every possible natural explanation, from stellar pulsations to instrumental artifacts before leaping to the supernatural or the extraterrestrial. This episode underscores the rigorous, self-correcting nature of the scientific process, where a bold claim is met not with dismissal, but with intense scrutiny, ensuring that our journey to understand the cosmos is built on a foundation of solid evidence rather than wishful thinking. While most of the signals we've explored so far emerged from the rigorous, peer-reviewed world of academic astronomy, some of the most persistent and intriguing stories come from a far more controversial intersection of science and speculation. One such story is the alleged 1973 signal from Zeta Reticuli, a tale forever entwined with one of the most famous UFO accounts in history. To understand this signal, we must first rewind to a dark New Hampshire road in 1961, where a married couple named Betty and Barney Hill experienced a terrifying event they would later describe under hypnosis as an abduction by non-human entities. During these sessions, Betty Hill recalled being shown a star map by her captors, a chart she later meticulously recreated from memory. This map, she said, showed the aliens' home system. Years later, a schoolteacher and amateur astronomer named Marjorie Fish took a deep interest in this star map, using beads and wires to construct a three-dimensional model of nearby sun-like stars. Fish spent years attempting to match the pattern Betty had drawn. Her startling conclusion, published in a 1973 issue of the Argosy UFO magazine, was that the map pointed to Zeta Reticuli, a wide binary star system about 39 light-years from Earth. Both stars are remarkably similar to our Sun, and the system quickly became a focal point for UFO enthusiasts. It was amidst this fervor that an extraordinary claim surfaced. Around the same time Fish's work was gaining attention, a mysterious, unexplained radio signal had been detected emanating from the direction of Zeta Reticuli. The specifics of this alleged signal are where the story enters a deep fog. Accounts of its frequency and duration are inconsistent, often varying dramatically between different retellings. Some versions describe it as a powerful, narrowband signal, while others suggest it was a complex pulse transmission. The most common narrative places its discovery within the military or a government agency, detected by a listening post and immediately classified due to its shocking point of origin. This lack of concrete, verifiable data is the primary reason the Zeta Reticuli signal is dismissed outright by mainstream astronomy. There are no published papers, no raw data sets, no official logs from any recognized observatory that can be independently analyzed. The signal exists primarily in hearsay, books on UFO phenomena, and the vibrant world of conspiracy theory. This places the Zeta Reticuli story in a unique and frustrating category. It's not a candidate for a technosignature in any scientific sense, but it's also more than just a random myth. Its power derives from its connection to the Hill case, creating a compelling, albeit entirely circumstantial, narrative loop. A woman draws a map under hypnosis, an amateur researcher matches it to a real star system, and then a signal is allegedly heard from that very system. This creates a satisfying story for those who believe, but for scientists, it's a classic case of building a conclusion on a foundation of unverifiable anecdotes. The skepticism isn't just about the signal itself, it's about the entire chain of events. Marjorie Fisher's interpretation of the star map has itself been heavily criticized by astronomers, who point out that the pattern of stars could be matched to any number of points in space depending on the viewer's perspective and the stars chosen for the model. Ultimately, the Zeta Reticuli signal occupies a strange liminal space. It is a cultural artifact, a powerful symbol of humanity's deep desire to find meaning and connection in the cosmos, to have our most fantastic stories validated by some form of evidence. It represents the point where the formal search for extraterrestrial intelligence, or SETI, brushes up against the wider, wilder world of ufology. For scientists, it's a cautionary tale about the perils of confirmation bias and the absolute necessity of rigorous, verifiable data. For believers, it's a piece of a larger puzzle, a hint that the truth might be hidden just beyond the reach of official acknowledgement. It remains a permanent part of the mystery's folklore, a signal that, real or not, continues to transmit a powerful message about our endless fascination with the question of whether we are truly alone. The quest to unravel the mystery of fast radio bursts has always hinged on one monumental challenge: pinpointing where they come from. For years, the vast majority of these signals were like cosmic gunshots heard in the night. We knew the blast was enormous, but we had no idea which window it had been fired from. This all began to change with the development of powerful new telescope arrays designed not just to hear these bursts, but to instantly triangulate their position with breathtaking precision. Enter the Deep Synoptic Array Prototype, or DSA-110, a collection of 110 individual radio dishes in California working in concert to act as a single, powerful eye on the sky. It was this cutting-edge instrument that captured a burst known as FRB 190523, and in doing so, it gave us a crucial piece of the puzzle that would both illuminate and complicate the entire FRB story. The most staggering fact about this particular burst is the sheer distance it traveled to reach us. By analyzing the subtle smear of its radio waves caused by traversing the intergalactic medium, a property known as dispersion measure, astronomers calculated its origin to be a galaxy an almost incomprehensible 7.9 billion light-years away. To put that into perspective, the burst we detected began its journey when our planet Earth was little more than a molten orb, and the most complex life forms were single-celled organisms. The energy required for a signal to remain so coherent and powerful across such a mind-boggling gulf of space and time is nothing short of phenomenal, reinforcing the idea that these events are among the most violent and energetic in the known universe. But the true revelation came when the DSA-110's precision allowed researchers to zoom in on the source galaxy itself. Unlike the host of the first repeating FRB, which was a tiny, primitive dwarf galaxy, the home of FRB 190523 was a massive, mature spiral galaxy, strikingly similar to our own Milky Way. This was a critical discovery. It proved definitively that fast radio bursts are not exclusive to one type of galactic environment. They are not just products of chaotic, star-forming dwarf galaxies. They can also originate in quieter, more evolved galaxies where the frenetic pace of star birth has significantly slowed down. This diversity of host environments immediately suggested a parallel diversity in the engines that power these bursts. There cannot be just one single explanation that fits all. The universe was telling us that multiple pathways can lead to these brilliant flashes. A further key distinction was what astronomers did not find when they looked at this galaxy. In the case of the first repeater, FRB 1212, follow-up observations revealed a faint, constant glow of radio emission lingering in the source region, a so-called persistent radio source. This suggested an engine that was continuously active, a central power source like a nebula or a supermassive black hole that was constantly energizing its surroundings. For FRB 190523, there was no such persistent emission. The region was radio quiet. This pointed toward a one-off cataclysmic event, the kind that destroys its source, such as the final merger of two neutron stars or the collapse of an overly massive star into a black hole. This new data created a significant challenge for the leading theory of the time, which revolved around magnetars. The repeating bursts had made a strong case for magnetars as a source, but could a young, highly magnetic neutron star be responsible for a blast in an old, settled galaxy where massive stars have not been born for eons? It seemed unlikely. Magnetars are the temperamental teenagers of the stellar world, born from the violent deaths of short-lived massive stars. They should not exist in great numbers in a galaxy that has grown old and quiet. The properties of FRB 1905-23 forced theorists to broaden their thinking, to consider that the one-off bursts and the repeating bursts might be fundamentally different phenomena altogether, perhaps requiring entirely separate catalogues and explanations. And of course, for those who look to the stars and wonder about intelligence, this burst presented its own quiet rebuttal. The sheer, raw power involved in a single event that can be seen across billions of light years is far beyond any conceivable technology. It would require energy equivalent to the total output of an entire star for decades, all focused into a millisecond flash. No known or theorized engineering could achieve this, making a technological origin for this particular signal effectively impossible. FRB 1905-23 stands as a monument to the power of precise observation. It didn't provide easy answers, but it gave us something even more valuable: clear boundaries. It showed us that the cosmos produces these incredible signals in a variety of ways, in a variety of neighborhoods, reminding us that nature's imagination is far wilder and more diverse than our own. Of all the cosmic mysteries we've encountered, perhaps none has captured the public imagination quite like the strange case of a single, unassuming star in the constellation Cygnus. This is KIC 8462852, more famously known as Boyajian star or Tabby star, named after the Yale astronomer Tabitha Boyajian, who first brought its bizarre behavior to the world's attention. While most of the signals we've discussed are fleeting bursts of radio energy, the mystery of Tabby's star is written in light, or more accurately, the perplexing and repeated absence of it. The story begins with NASA's Kepler Space Telescope, a revolutionary observatory designed to find planets by staring unblinkingly at one patch of sky, measuring the tiny, periodic dips in starlight that occur when an orbiting planet crosses in front of its host sun. Kepler monitored over 150,000 stars, and the data was meticulously sifted by both professional astronomers and a legion of citizen scientists in the Planet Hunters project. It was these dedicated amateurs who first flagged this particular star as bizarre and interesting, setting in motion one of the most captivating astronomical detective stories of the century. The data revealed by Kepler was unlike anything ever seen. Planets cause predictable, symmetrical dips in brightness that repeat like clockwork. Tabby's star displayed something entirely different. It underwent deep, irregular dimming events where its light output would plummet by up to 22%, an absolutely staggering amount. To put that in perspective, a Jupiter-sized planet, the largest in our solar system, would block only about 1% of a sun-like star's light. These dips were not only deep but also asymmetrical and aperiodic, with no discernible rhythm or pattern. Some lasted for days, while others stretched on for weeks. The most famous of these, dubbed the Dyson dip, saw the star's brightness drop gradually and then rapidly snap back, a profile that looked nothing like a spherical body transiting a star. It was as if something massive, complex, and oddly shaped was passing in front of it, blocking its light in a chaotic and unpredictable dance. Faced with such an unprecedented signal, the scientific community did what it always does: it began proposing theories. The initial and most natural explanation involved a massive swarm of comets. The idea was that a family of exocomets, perhaps disrupted by the gravity of a passing star, had been drawn in close to Tabby's star. As they broke apart, they could create a vast, dusty cloud of debris that would occlude the star's light in irregular clumps, potentially explaining the strange dimming patterns. While this was a valiant effort to explain the mystery with known physics, many researchers found the model strained. To create dips that deep, the number of comets required would be almost unimaginably vast, numbering in the hundreds of thousands or even millions, pushing the idea of a natural swarm to its absolute limit. It was this tension between highly implausible natural models and the seemingly impossible that opened the door for a more speculative, yet irresistibly fascinating idea, the alien megastructure hypothesis. The concept, first proposed by physicist Freeman Dyson, suggests that a sufficiently advanced civilization, having exhausted the energy resources of its home planet, might eventually construct a vast array of energy-collecting satellites, a Dyson sphere, encircling its star to harness its total power output. A partially completed or rotating swarm of such structures would be irregular, non-spherical, and would block starlight in exactly the kind of bizarre, aperiodic way that Kepler observed. For the first time in modern astronomy, a serious, peer-reviewed paper was discussing the possibility that we might be seeing evidence of astroengineering, the literal works of an alien civilization. This was not a wild claim from the fringe. It was a hypothesis put forward to explain data that stubbornly resisted all conventional explanations, and it instantly catapulted Tabby's star from an academic curiosity to a global sensation. Inevitably, the search for extraterrestrial intelligence trained its instruments on the star, hoping to find a more definitive technosignature. The Breakthrough Listen project used the Green Bank telescope to scan for narrowband radio signals that would be the hallmark of intentional communication or radar. They also searched for broadband signals that might be leakage from powerful technologies like intense propulsion systems. The initial results, however, were a profound silence. No telltale radio transmissions were found, but the story didn't end there. A subsequent analysis of older data from the Buckwheat Optical SETI Observatory in Panama claimed a detection of several incredibly short, intense laser pulses from the direction of Tabby's star. These claims were met with significant skepticism, as the signals were faint and have never been replicated. The overall radio silence was initially seen as a point against the intelligence hypothesis, but proponents were quick to counter. A civilization capable of building a megastructure would likely be millions of years more advanced than us, and might use communication technologies so sophisticated that we wouldn't even recognize them as signals, or perhaps they simply aren't broadcasting. Direction. The debate raged on, fueled by further observations that only deepened the mystery. Ground-based telescopes confirmed that the star wasn't just dipping erratically, it was also undergoing a long-term secular dimming. Over the course of a century, according to archival data from old photographic plates, Tabby's star appears to have faded by a significant amount. This combination of short-term, deep dips and a long-term fade is exceptionally difficult to reconcile with any single, simple theory. The scientific process has continued to grind away at the problem, and a consensus has begun to lean towards a natural, albeit exotic, explanation. The most promising theory today involves an immense cloud of extremely fine, sub-micron-sized dust particles orbiting the star. This kind of dust is highly effective at blocking light and could explain both the deep, irregular dips and the long-term dimming without requiring the presence of solid, opaque objects like megastructures. The origin of this dust, whether from a catastrophically shattered planet, a colossal collision of asteroids, or some unknown stellar process, remains its own compelling mystery. Yet, despite the leaning towards a dusty answer, Tabby's star retains its powerful grip on our curiosity. It represents a perfect storm of scientific intrigue, a genuinely anomalous signal, a plausible but thrillingly speculative hypothesis, and a mystery that unfolded in real time, allowing the public to participate in the scientific process. It taught us that the universe is still full of surprises that can challenge our assumptions and force us to consider possibilities at the very edge of imagination. Even if the answer ultimately turns out to be a colossal cloud of space dust, the journey it took us on, the serious contemplation of whether we might be seeing the handiwork of another intelligence, has forever changed the conversation and proven that the most exciting signal is sometimes the one that doesn't make any sense at all. While the debate over Tabby's star was captivating scientists and the public alike, another signal from the archives of Arecibo continued to intrigue researchers for its own set of compelling and unresolved characteristics. In 1997, the iconic telescope was engaged in a systematic survey of Messier 13, a magnificent globular cluster located 25,000 light-years away in the constellation Hercules. This dense ball of hundreds of thousands of ancient stars was considered a prime target for the search for extraterrestrial intelligence. The logic was sound. If an advanced civilization wanted to broadcast its existence, a densely populated and stable region like a globular cluster would be an ideal place to erect a powerful, long-lasting beacon that could be seen across the galaxy. It was during this patient search that the telescope's computers flagged something extraordinary, a signal so unusual it was immediately given the highest priority for analysis. What made this detection so remarkable were its pristine, artificial-like qualities. The signal was a perfect example of a narrowband transmission, meaning its energy was concentrated into an incredibly tight slice of the radio spectrum. In nature, cosmic events like pulsars or stellar flares produce radio emissions that are broadband, smeared across a wide range of frequencies like static on a television. This signal was the opposite, a laser-sharp spike on a single frequency, which is a hallmark of engineered technology designed to punch through the background noise of the universe with maximum efficiency. The specific frequency it occupied only added to the mystery. It was detected at 1420 MHz, the universal hydrogen line, the very same frequency that had made the WOW signal so famous. This is the cosmic equivalent of a clear, open channel, a frequency any technologically advanced species would recognize as a logical place to listen and to call out. The signal's behavior was both thrilling and frustrating. It was incredibly strong, far above the background noise, and it appeared to drift in frequency in a way that was consistent with the rotation of the Earth. This drift is a key test used to distinguish celestial sources which move smoothly across the sky from terrestrial interference, which typically remains fixed in frequency. For a brief, heart-pounding moment, it passed this initial filter, suggesting an origin beyond our planet. The team at Arecibo was electrified. Standard protocol demanded immediate verification. The procedure was to swing the massive telescope away from the target for a few minutes and then point it back. A genuine celestial signal would disappear when the telescope was off source and then reappear when it was pointed back at the exact same coordinates. Human-generated interference, by contrast, would typically remain constant regardless of where the telescope was aimed. This is where the story of the 1997 Arecibo signal takes a frustrating turn. The team executed the verification maneuver, moving the giant dish away from M13 and then back. But when they looked back at the data, the signal was gone. It never returned. It had lasted for less than a minute, a fleeting whisper that vanished before its nature could be confirmed. This brief duration is the central reason the signal remains an enigma to this day. Without that second look, without the ability to observe it again, scientists were left with a single, tantalizing data point that could neither be verified nor fully dismissed. In the absence of confirmation, the most likely explanation became terrestrial interference. The 1420 MHz band is not exclusively reserved for astronomy. It is also used by satellites and other human technologies. The most probable culprit was believed to be a secret military or communications satellite, one whose transmissions were not publicly documented. Such a satellite passing through Arecibo's field of view could have produced a strong, narrowband signal that exhibited the correct Doppler drift, perfectly mimicking a celestial source. It was a cruel cosmic prank, a case of our own technology masquerading as the very thing we were searching for. Despite this probable explanation, the signal's impact on the field of SETI was profound and lasting. It served as a critical lesson in the challenges of real-time detection and verification. The experience underscored the vital importance of having multiple telescopes available to instantly follow up on a promising candidate. If another dish had been observing the same point in the sky at the same time and had also detected the signal, its extraterrestrial origin could have been confirmed. This event directly influenced the development of new observational strategies, pushing the community toward creating networks of telescopes that can work in concert to provide immediate confirmation and rule out terrestrial false alarms. It also led to more sophisticated data analysis techniques, with improved algorithms designed to filter out known sources of human-made radio frequency interference with greater accuracy. The 1997 signal may forever remain unconfirmed, but its legacy is a sharper, more robust, and more prepared search for answers to humanity's oldest question. Just when we thought we had fast radio bursts neatly cornered as intergalactic phenomena, the universe delivered a surprise from our own cosmic backyard, a detection so close and so bizarre it forced a complete re-evaluation of where these incredible explosions can occur. This is the story of FRB 2020-00120E, a burst that broke all the rules by coming not from a distant galaxy, but from within the familiar confines of our own Milky Way. Discovered in 2020 by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, this signal immediately stood out for one simple reason: its dispersion measure was astonishingly low. Unlike the vast majority of FRBs that show the unmistakable smear of a multi-billion light-year journey, this one had traveled through so little material that its source had to be incredibly nearby, a mere 12 million light-years away. This placed it well within our local galactic neighborhood, making it the closest FRB ever detected and offering an unprecedented opportunity to study one of these events up close. The real shock came when an international team of astronomers using a network of ultra-precise telescopes managed to pinpoint its origin with breathtaking accuracy. They traced the burst not to a star-forming region in a spiral arm, but to a completely unexpected and theoretically hostile environment, a globular cluster orbiting the majestic spiral galaxy M81. Globular clusters are among the oldest structures in the universe, dense balls of hundreds of thousands of stars that formed over 12 billion years ago during the universe's infancy. They are cosmic retirement homes filled with ancient, low-mass stars like red dwarfs and the faded remnants of dead stars, white dwarfs and pulsars. They are famously lacking in the raw materials needed to create new stars, the massive, short-lived stars that die in the supernova explosions required to birth neutron stars and magnetars vanished from these clusters eons ago. Finding an FRB here was like finding a newborn baby in a medieval castle. It simply shouldn't be possible based on everything we thought we knew. This precise localization sent a tremor through the field of astrophysics. The leading theory for most repeating FRBs had firmly settled on magnetars, incredibly dense, highly magnetized neutron stars that are the temperamental teenagers of the stellar world, born from the violent deaths of massive stars. But massive stars don't exist in globular clusters. They burned out and died billions of years ago. So what could possibly be the engine for this incredibly energetic event in a place where the fuel for such engines ran out long ago? Astronomers were confronted with a paradox that demanded new thinking. The resolution to this puzzle appears to lie in the unique and dynamic environment of the globular cluster itself. While it's true that new massive stars aren't born there, these dense environments are breeding grounds for a different kind of stellar drama, stellar collisions and mergers. In the crowded core of a globular cluster, stars can gravitationally interact, sometimes forming tight binary systems or even colliding outright. The leading theory for FRB 200120E posits that it was not born from a young magnetar, but from a highly evolved stellar corpse that found a new lease on life through a violent encounter. One compelling model suggests the source is an accreting neutron star, a pulsar that has stolen material from a binary companion, perhaps a white dwarf. As this stolen matter builds up on the neutron star's surface, it can trigger immense thermonuclear explosions or cause starquakes that release the colossal bursts of energy we see as FRBs. Another, even more exotic possibility is that the source is a magnetar after all, but one that was formed through a completely different pathway. The merger of two white dwarfs, or the accumulation of material onto a white dwarf that pushes it over the Chandrasekhar limit, causing it to collapse not into a standard neutron star, but directly into a magnetar. This born-again magnetar would be a stellar zombie, a newly created energetic object in a place where nothing new was supposed to exist. The detection of a faint, persistent radio source at the precise location of the burst lends strong support to these binary interaction models, suggesting an ongoing engine at the site, continuously active and capable of producing multiple outbursts. This single, nearby signal fundamentally expanded our understanding of the cosmic factories that can produce fast radio bursts. It proved that FRBs are not just the domain of young, star-forming galaxies. They can also erupt in the oldest, quietest neighborhoods in the universe. This means the conditions to create these spectacular events are far more diverse and universal than we ever imagined. FRB 200120E taught us that even in the cosmic geriatric ward, there's enough latent energy and gravitational potential for a spectacular outburst, a testament to the fact that the universe always has a new way to surprise us. While the story of SETI 02+14 often takes center stage as the primary candidate from the SETI at Home project, its mystery is deeply intertwined with a handful of other, lesser-known signals detected during the same period. These companion detections form a curious and often overlooked subplot in the larger narrative. The original analysis didn't just identify one anomalous signal. It flagged a small cluster of them, all sharing eerily similar characteristics. Each of these signals was also narrowband, and each exhibited that same tantalizing Doppler drift, the subtle shift in frequency that mimics what you would expect from a transmitter on a rotating planet. This wasn't just one voice calling out. It was as if a small choir was singing the same song from different parts of the stage. The statistical implications of this cluster were profound. Finding one signal with these specific, artificial-seeming properties could be written off as a remarkable fluke, a one-in-a-million combination of random noise. But finding several of them, all emerging from the same dataset and sharing the same technical signature, suggested something more. It raised the compelling, albeit speculative, possibility that these weren't isolated false alarms but related phenomena. Perhaps they were multiple transmissions from a single source, or beacons from different locations within the same star system, or even a coordinated effort across several civilizations. The data seemed to whisper of a pattern, a coherence that begged for a unified explanation beyond mere coincidence. This apparent pattern, however, ran headlong into the most significant counter-argument, the specter of instrumental artifacts. The SETI at Home project was a monumental achievement in distributed computing, but its methodology had inherent vulnerabilities. The data was processed on millions of different home computers, each with slightly different hardware, software, and background processes. Critics argued that this entire cluster of signals could be the product of a subtle, systemic glitch within the processing software itself. A single bug in the algorithm, or a common type of interference generated by a popular model of computer processor, could theoretically produce a series of nearly identical false positives. These signals weren't being heard by a single controlled instrument. They were being heard by a vast and varied network, making it incredibly difficult to rule out a digital gremlin common to the system. Furthermore, the very nature of their detection made traditional verification impossible. Unlike a signal detected by a single radio telescope, which can be immediately re-observed, these signals were processed after the fact. The moment of their potential transmission had long passed by the time the data was analyzed, meaning there was no chance to point another dish at the coordinates to listen for a repeat performance. They were frozen in the data, immune to the follow-up observations that are the bedrock of scientific confirmation. Their existence is purely archival, a series of intriguing footnotes in a much larger report. This combination of factors is why these companion signals ultimately deepened the mystery of SETI 02+14, rather than resolving it. They provided neither clear confirmation nor definitive refutation. If they were real, they suggested a phenomenon more complex and widespread than a single beacon. But if they were artifacts, they cast a long shadow of doubt over the entire dataset, including the flagship signal itself. They exist in a frustrating limbo, too statistically curious to be easily dismissed, yet too technically ambiguous to be embraced as evidence. They remain a permanent part of the lore, a reminder that in the search for cosmic company, sometimes the noise can form patterns that are just as compelling and just as haunting as the signal we hope to find. The journey into cosmic mysteries isn't confined to the distant depths of space. Sometimes it arrives right on our doorstep, carried on the back of a silent, icy traveler from another star system. In late 2019, the astronomical community was electrified by the arrival of 2I Borisov, the first confirmed interstellar comet ever observed passing through our solar system. Unlike its predecessor, the bizarre and rocky Oumuamua, Borisov was a more familiar sight, a classic comet, complete with a visible coma and tail of gas and dust as it swung around the sun. This visitor from the void presented an unprecedented opportunity, a chance to study the composition of a world formed around another star, and for a small group of researchers, a unique moment to listen. As Borisov made its closest approach to Earth, coming within roughly 190 million miles, a team using the Allen Telescope Array in California turned its dishes toward the object. Their goal wasn't to find aliens, but to conduct a novel experiment, to see what kind of radio emissions a comet from another star might naturally produce. To their surprise, their initial analysis of the data suggested they had detected something, a faint radio signal at a specific frequency. The news, as it often does in the modern age, quickly escaped the confines of academic circles and ignited a firestorm of speculation online. Had we just detected a transmission from an interstellar probe, the frequency of the alleged signal became a central point of intense debate. The claims centered on a detection around 142 GHz, a band that is notably occupied by a specific emission line of a molecule called formaldehyde. While formaldehyde is known to exist in molecular clouds in space, its detection as a strong, coherent emission from a single, small object like a comet would be highly unusual. For those hoping for a more extraordinary explanation, this frequency band also sits within what is known as the microwave window, a range of the spectrum that is theoretically well suited for interstellar communication due to its relatively low background noise. The coincidence was tantalizing, and for a brief moment, it seemed as if the most fantastic scenario might be possible. This initial excitement ran headlong into the rigorous skepticism of the broader scientific community. Other radio telescopes, including the mighty Robert C. Byrd Green Bank Telescope in West Virginia, also observed Comet Borisov during its passage. Their findings were definitive. They detected no unusual radio signals whatsoever. The consensus among most astronomers was that the original detection was almost certainly a case of instrumental noise or terrestrial interference mistaken for a cosmic source. The Allen Telescope Array is an incredibly sensitive instrument, but it is also situated in an environment increasingly flooded with human-made radio signals from satellites to wireless networks. Filtering out this ever-present background hum is one of the most significant challenges in modern radio astronomy. The episode, while ultimately likely a false alarm, served as a critical and sobering lesson for the field. It highlighted the immense difficulty of studying transient, moving objects, especially those that pass through our neighborhood only once. A comet moves quickly against the backdrop of the stars, and its Doppler shift, the change in frequency caused by its motion, is complex and constantly changing. This makes it exceptionally difficult to distinguish a potential signal originating from the comet itself from a fixed source of interference on Earth that the telescope's electronics might be picking up. The Borisov incident underscored the absolute necessity of immediate, independent verification by multiple observatories for any such claim. Beyond the technical challenges, the event also sparked a fascinating philosophical discussion about the nature of future discoveries. If a genuine, artificial signal were ever detected from an interstellar object, how would we even begin to verify it? We couldn't simply wait for it to pass by again in a few years. It would be gone forever, a single, fleeting chance at contact. The pressure to analyze the data and draw conclusions would be immense, and the risk of error would be extraordinarily high. The story of the Borisov signals, though likely a story of human error rather than alien contact, provided a valuable dry run for this very scenario. It tested our protocols, our instruments, and our collective composure, reminding us that the greatest challenge in finding a signal from the stars may not be hearing it, but knowing for certain that what we heard was real. Deep within the chaotic heart of our own galaxy, where the pull of a supermassive black hole warps the very fabric of space-time, another mystery was quietly broadcasting its presence for years before we finally learned to listen. This is the story of JWST J1745-3009, a celestial object so enigmatic that its very name reveals its location, galactic center radio transient, and its baffling behavior. Unlike the distant, extragalactic fast radio bursts that arrive in milliseconds, this signal was a slow, rhythmic drumbeat from our own cosmic backyard, a pulse that defied classification and has stubbornly refused to be seen again. Its discovery was a classic case of finding something you weren't actively looking for. Back in 2002, a team of astronomers was carefully analyzing archival data from the Very Large Array Radio Telescope in New Mexico, gathered during a survey of the galactic center. Sifting through the intense radio noise generated by swirling gas clouds and powerful magnetic fields, they stumbled upon a series of incredibly bright, coherent bursts. These weren't the faint, scattered emissions of a distant quasar. They were giant, luminous pulses that would appear suddenly, last for about 10 minutes, and then vanish. The most astonishing feature, however, was their timing. These spectacular bursts repeated with a precise 77-minute period. It was a cosmic clockwork mechanism operating in the most hostile neighborhood of the Milky Way. The intensity of these bursts immediately set JWST J1745-3009 apart from any known class of object. To shine so brightly in the radio spectrum, the source had to be phenomenally energetic. At first glance, the natural assumption was that it must be some new kind of pulsar, a rotating neutron star that beams radiation across space like a lighthouse. But this is where the comparison breaks down. Normal pulsars rotate incredibly fast, some hundreds of times per second, their pulses arriving in a rapid metronomic tick. A period of 77 minutes is glacial by comparison. It's slower than the rotation of most planets. No neutron star, not even the most lethargic, spins that slowly. Furthermore, typical pulsars are remarkably consistent in their output, while this source was almost entirely quiet, only flaring up dramatically during its brief 10-minute active window in its cycle. It was a radio star that spent over an hour sleeping and just 10 minutes screaming. Faced with such a paradoxical set of characteristics, theorists had to get creative. The leading explanation involves a phenomenon known as precession. Imagine a spinning top just as it starts to wobble and slow down. That wobble is precession. Now apply that to an immensely magnetic neutron star, a magnetar. If such an object is precessing, if its rotation axis is slowly tracing a circle in space, then the powerful beam of radio waves it emits would only sweep across Earth for a small fraction of that precession cycle. This could perfectly explain the long 77-minute period and the short, brilliant burst window. We're not seeing the star's rotation speed, we're seeing the much slower wobble of its entire body, and we only get a flash of its energy when the wobble points its beam in our direction. Another compelling theory suggests this object could be a special type of interacting binary system. Picture a highly magnetic white dwarf or a neutron star in a wide orbit with a common, low-mass star. As the magnetic star moves through its orbit, its immense field could periodically interact with the atmosphere or stellar wind of its companion, funneling material onto its magnetic poles. This sudden dumping of matter could trigger a brief, intense thermonuclear explosion on the surface, unleashing the colossal radio burst we observe. The orbital period of the binary would then dictate the timing, explaining the strict regularity. This model turns the source from a solitary, wobbling star into one half of a dramatic cosmic partnership. Perhaps the most intriguing aspect of this mystery is its solitude. Despite 2 decades of extensive and dedicated searches of the galactic center with ever more sensitive telescopes, not a single other object like JWST 1745-3009 has ever been found. It remains a one-of-a-kind anomaly. This profound loneliness suggests one of 2 possibilities. Either we were incredibly lucky to catch it during a brief active phase in its life, and it has since settled into a permanent quiet state, or these objects are extraordinarily rare, representing a brief transitional stage in the life of a neutron star that few objects ever pass through. It serves as a powerful reminder that even within our own galaxy, there are still unique and undiscovered phenomena lurking in the shadows, waiting for another moment to reveal themselves and challenge our understanding of the cosmos. If the silent travel of Borisov presented a puzzle of potential signals, the arrival of our very first interstellar visitor just 2 years earlier presented a mystery defined by its profound and unexpected silence. In October 2017, the Pan-STARRS telescope in Hawaii spotted a strange object hurtling through our solar system at high speed. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity. It was a visitor from another star system just passing through. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. Its appearance was immediately thrilling, but its physical characteristics were baffling. Light curve measurements suggested it was highly elongated, shaped like a cigar or a pancake, and it was tumbling end over end. Most bizarrely, as it traveled away from the sun, it exhibited a slight but undeniable non-gravitational acceleration, as if something other than gravity was giving it a tiny push. The scientific community was electrified, and the Breakthrough Listen project saw a historic opportunity. Within days of its discovery, the team behind the initiative swiftly mobilized the powerful Green Bank telescope in West Virginia. The logic was sound and deeply exciting. Here was our first confirmed sample of an interstellar object. If it were a natural asteroid or comet, it would be inert, a silent rock. But if it were something more, perhaps an artifact or a derelict probe from another civilization, it might still possess some functioning technology, and that technology might be leaking radio waves or even actively transmitting. For a total of 6 hours across 4 radio bands, Green Bank listened intently, scanning for any sign of artificial emission. The entire astronomical world waited for the results, anticipating even the faintest whisper from this cosmic scout. The results, however, were a profound and puzzling silence. Breakthrough Listen detected absolutely nothing. No narrowband signals, no broadband leakage, not even the faint natural radio emissions that many scientists expected to detect from any sizable object traveling through space. This complete radio quiet was in itself a significant anomaly. It suggested that Oumuamua was either incredibly inert, lacking the kind of metallic or ionic composition that would generate natural radio signatures, or it was somehow engineered to be radio silent. This eerie silence only deepened the mystery surrounding the object's strange acceleration and peculiar shape, forcing researchers to consider a wider, weirder range of possibilities for what it could be made of. Amid this overwhelming quiet, however, a few brief, intermittent signals were noted in the data. These were not the sustained, narrowband transmissions one would hope for. They were fleeting spikes, so faint and short-lived that they were initially dismissed as noise. Yet, a few researchers pointed out a curious correlation. These brief, unverified blips seemed to coincide with the period of Oumuamua's chaotic tumbling motion. The hypothesis was tantalizing. If the object were a derelict spacecraft with damaged, asymmetrical panels or antennas, its tumbling could cause those pieces to occasionally reflect sunlight or even produce a sporadic, distorted burst of radio energy in our direction. It would be like a lighthouse with a broken lamp, only flashing a beam of light at random, unpredictable intervals as it spun. While this idea was purely speculative and never confirmed, it highlighted the object's ability to inspire creative solutions to its many puzzles. The ultimate resolution to the Oumuamua enigma remains one of the most active debates in astronomy. The leading natural explanation proposes that it was a novel type of extremely porous, fluffy asteroid made of ices like solid nitrogen or hydrogen. As it passed close to the Sun, these ices would have sublimated, turned directly from a solid to a gas, providing the tiny thrust that explained its acceleration without producing the visible coma or tail of a typical comet. This would also account for its strange shape and lack of radio emissions. However, this theory is not without its own problems, and some prominent scientists maintain that we cannot yet rule out more exotic origins. Oumuamua's legacy is not a definitive answer, but a powerful lesson in humility. It taught us that the universe is capable of producing objects that defy our existing categories, and that our first interstellar messenger may have delivered its most important message not in a signal, but in its silence, a quiet reminder of how much we have yet to learn. Yet, even as the scientific consensus coalesced around a human-made origin for BLC-1, the story from our nearest stellar neighbor was far from over. In the months that followed that initial, electrifying detection, the Breakthrough Listen team continued their meticulous analysis of the vast dataset collected from Proxima Centauri. To their astonishment, they found not just one intriguing signal, but several more. These new candidates, while fainter and less headline-grabbing than BLC-1, presented a fresh and even more complex layer to the mystery. They were not clustered on a single frequency. Instead, they appeared at different points across the radio spectrum, each with its own unique signature. Some were narrowband like their predecessor, while others exhibited slightly wider bandwidths or different patterns of drift. This wasn't a single voice calling out. It was beginning to look like a chorus of whispers, or perhaps the scattered transmissions of a noisy technological civilization. The existence of multiple signals from the same system fundamentally altered the debate. A single instance of bizarre interference, no matter how compelling, can often be dismissed as a one-in-a-million fluke. But finding a handful of them, all emanating from the direction of the same star system, forces a much more difficult statistical calculation. What are the odds that several different pieces of human technology would all conspire to create spurious signals that just happen to point back to Proxima Centauri, and only when the telescope was looking at it? This pattern started to look less like random coincidence and more like a persistent phenomenon with a single, localized source. For the researchers involved, it reopened the door to possibility, however cautiously. Could BLC1 have been just the brightest and most obvious member of a larger family of genuine transmissions? The notion that we might be detecting not a simple beacon, but the generalized radio leakage from an entire civilization, the equivalent of our own television broadcasts, radar, and satellite communications all combined, suddenly seemed less like science fiction and more like a hypothesis that needed to be seriously, rigorously addressed. Of course, the other side of the argument is equally compelling, and it delves into the arcane world of radio frequency interference. The new signals, with their varied frequencies, actually strengthen the case for a complex terrestrial origin. The modern radio environment is a crowded and chaotic place, a jungle of transmissions from cell phones, satellites, aircraft, military radar, and countless other sources. These signals don't just travel in straight lines, they can bounce off the ionosphere, reflect off aircraft or satellites, and even intermodulate, a process where two strong signals mix inside the slightly imperfect electronics of the telescope itself to create a phantom, third signal at a completely new frequency. Proxima Centauri, as the closest star system, is a prime target for observation and is therefore looked at often. It is statistically more likely that over many hours of observation, the complex, swirling mess of human radio pollution would occasionally align to produce not just one, but several false positives that all appear to originate from that same point in the sky. In this view, the multiple signals aren't evidence of aliens, they are evidence of our own technological immaturity and the incredible difficulty of filtering our own noise out of the cosmic signal. This ongoing debate has ensured that Proxima Centauri remains one of the most intensely watched stars in the sky for SETI researchers. The disappointment of BLC1 has been replaced not with abandonment, but with a renewed and more sophisticated focus. Astronomers now understand that the real work isn't just about finding a signal. It's about understanding the intricate fingerprint of human interference at each and every observatory. They are developing new algorithms and verification techniques specifically designed to catch the kind of complex intermodulation that likely created these signals. Every new observation of Proxima adds to a growing database of what noise looks like from that direction, making it easier to identify future anomalies. Furthermore, the discovery of a second planet, Proxima d, and the potential existence of a complex system of worlds around the star only adds to the motivation. A multi-planet system could host a spacefaring civilization, its traffic and communications creating the very kind of multiple, varied signal sources that appear to be present. The whispers from next door, whether they are ultimately proven to be celestial or terrestrial, have cemented Proxima Centauri's status as a constant reminder that the answer to our oldest question might be hiding in the place we'd least expect to find a secret, right in our own backyard. Amid the intense technological rivalry of the Cold War, where space was the ultimate battlefield for prestige, a different kind of arms race was taking place, a quiet, listening race. While American projects like SETI were publicly known, the Soviet Union was conducting its own extensive search for cosmic intelligence, often shrouded in the secrecy that defined the era. It was within this clandestine environment that one of the most compelling and politically charged detections occurred. In 1976, a team of Soviet radio astronomers using the massive Ratan 600 telescope, a unique ring-shaped array in the Caucasus Mountains, detected a powerful, enigmatic signal that seemed to perfectly match the profile of an extraterrestrial broadcast. The event was immediately classified, treated not just as a scientific curiosity but as a matter of state security. The signal's technical characteristics were what made it so extraordinary to the scientists who heard it. It was a strong, narrowband transmission, a hallmark of technology, and it appeared to be emanating from a point near the star HD 164595 in the constellation Hercules, a sun-like star that would later be the source of another mysterious signal. But the most compelling feature was its behavior. As the Earth rotated and the telescope's beam swept across the sky, the signal demonstrated a clear attenuation pattern. It grew stronger as it moved into the center of the telescope's field of view and then faded as it moved out. This precise directional characteristic is a key test for a genuine celestial source, as it effectively rules out terrestrial interference, which typically bleeds into the receiver regardless of where the dish is pointed. For the Soviet team, this was the most convincing evidence they had ever encountered. The political climate of the 1970s ensured that this discovery would be handled with extreme caution. In the midst of the Cold War, the potential implications of such a detection were staggering. Confirming contact with an extraterrestrial intelligence would have been the ultimate propaganda victory, a cosmic coup that could shift the global balance of prestige. Conversely, announcing a false alarm could lead to international embarrassment and ridicule. The information was deemed so sensitive that it was reportedly brought to the attention of the highest levels of the Soviet government. A strict policy of secrecy was enforced, with details kept within a very small circle of academics and officials. This secrecy had a profound effect. It prevented the kind of open, international scientific scrutiny that is essential for verifying such an extraordinary claim. American astronomers, who might have been able to point the Arecibo or Green Bank telescopes at the coordinates for immediate confirmation, were kept entirely in the dark. The legacy of the 1976 Soviet signal is not one of confirmation, but of profound and lasting influence. While the raw data and full analysis were never formally published or shared with the West, rumors and fragmented accounts of the event seeped out over the years, creating a persistent legend within the SETI community. For Soviet scientists, the experience underscored the necessity of developing more robust verification protocols and arguably fueled a more determined, if still often secretive, pursuit of the search within the Eastern Bloc. For their American counterparts, the whispers of a near miss by the Soviets served as both a cautionary tale and a motivator. It highlighted the paralyzing effect of political isolation on scientific progress and reinforced the American commitment to a more open, collaborative approach to SETI, in the hope that the next potential detection could be instantly verified by a global network of telescopes. The signal itself remains an enigma, a ghost in the machine of Cold War history, its truth locked away in forgotten archives, a permanent reminder of how earthly conflicts can shape our search for answers among the stars. For years, the enigmatic phenomenon of fast radio bursts seemed to follow an unspoken rule. They lived in the high-rent district of the radio spectrum. These millisecond cosmic flashes had only ever been detected at frequencies above 700 MHz, with most occurring well above 1 GHz. This pattern led many astrophysicists to suspect a fundamental physical limit was at work. The prevailing theory suggested that lower frequency radio waves might be simply too weak to make the epic journey across intergalactic space, their signals smothered and scattered into oblivion by the diffuse plasma between galaxies before they could ever reach our telescopes. It was a convenient, tidy explanation that placed a theoretical flaw beneath which we wouldn't expect to hear anything at all. But the universe has a habit of breaking our most comfortable assumptions. On a summer night in 2018, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, was undergoing commissioning tests, its systems still waking up. Even in this preliminary phase, its revolutionary design, a stationary array with an enormous field of view, proved its worth. It detected a burst that would send a ripple through the field of radio astronomy, designated FRB 180725A. The burst itself was unremarkable in its duration and structure, a fleeting shout in the darkness lasting mere milliseconds. Its revolutionary feature was its address on the dial. it was detected at 580 MHz, shattering the supposed minimum frequency threshold by a staggering margin. This wasn't just a little lower, it was a door kicked open into an entirely new room of the cosmic radio mansion. The immediate implication was a direct challenge to our understanding of how these signals propagate. The lower the frequency of a radio wave, the more susceptible it is to an effect called dispersion, where intervening free electrons in space cause the wave to scatter and smear. The fact that this burst not only survived its journey but arrived at our telescopes with a coherent structure meant that the intergalactic medium it traveled through was less dense or turbulent than our models predicted. It forced a recalibration of those models, suggesting the pathways between galaxies might be clearer, or the bursts themselves even more inherently powerful than we had ever imagined. This single detection expanded the playing field, proving that these events could punch through the noise across a much wider band of the radio spectrum than we thought possible. This breakthrough had a profoundly practical impact. It dramatically increased the number of instruments that could join the hunt. Lower-frequency radio telescopes are generally less expensive and more numerous than their gigantic high-frequency counterparts. The detection validated a whole class of existing telescopes that had previously been considered irrelevant to the FRB search. Almost overnight, observatories around the world that were designed to study pulsars or map hydrogen in our own galaxy could now retask some of their efforts to listen for these cosmic interlopers at new frequencies. It democratized the search, inviting a global community of astronomers to point their dishes toward the mystery. Perhaps most importantly, FRB 180725 opened a new window for comparative study. By detecting the same burst at both high and low frequencies, astronomers could perform a kind of cosmic spectroscopy on the signal itself. The way the burst's properties changed across the spectrum would provide vital clues about the environment immediately surrounding its source, the material it passed through, and the fundamental emission mechanism that generated it. It was like being able to hear a musical note not just as a single pitch, but across multiple octaves simultaneously, each one revealing a different part of the instrument that created it. This low-frequency pioneer proved that to truly understand these brilliant flashes, we must listen to the entire symphony of the radio universe, from the deepest bass notes to the highest treble, because each frequency holds a unique piece of the puzzle. While the search for cosmic messages has largely been a story of radio telescopes and computer algorithms, there exists a far more controversial corner of this endeavor, one that ventures from the clean rooms of astrophysics into the murky world of the paranormal. This is the strange tale of what some have called extraterrestrial voice phenomenon, a series of alleged detections in the late 1990s that claim to have recorded something astonishing. Not structured data or mathematical pulses, but audio-like signals from the depths of space. These claims did not emerge from a major observatory, but from the work of individual researchers using unconventional methods on publicly available data, and they sit at a deeply uncomfortable intersection between rigorous science and speculative belief. The methodology behind these detections was fundamentally different from standard radio astronomy. Instead of searching for narrowband signals or dispersed bursts, these researchers applied audio processing techniques to raw radio telescope data. They would take the seemingly random cosmic static, often from sources like pulsars or the galactic center, and run it through various software filters, slowing it down, shifting its frequency, compressing its dynamic range, and enhancing certain harmonics. The goal was to make the inaudible audible, to bring signals that were naturally far below the range of human hearing into a spectrum our ears could perceive. Proponents argued that this was a valid form of analysis, akin to using a microscope to see otherwise invisible details, suggesting that an advanced civilization might encode information in these subtle audio frequency modulations. What they reported hearing after this extensive electronic massage of the data were sounds they described as eerie, choppy, and vaguely vocal, like fragmented whispers, metallic chirps, or even what some passionately believed were distinct syllables and words. The immediate and obvious comparison is to terrestrial electronic voice phenomenon, or EVP, a practice popular in paranormal circles where enthusiasts claim to hear the voices of spirits in recorded white noise. The parallels are striking. In both cases, raw, random noise is heavily processed until the human auditory system, which is evolutionarily hardwired to find patterns, especially voices, begins to perceive structure where none may exist. This psychological effect is known as audio pareidolia. It's the same phenomenon that causes us to hear words in the backward masking of a song or see faces in the patterns of a marble wall. Our brains are magnificent pattern recognition engines, but they are also prone to false positives, especially when primed by expectation and belief. Mainstream radio astronomers pointed to this as the most likely explanation, arguing that the described signals were nothing more than auditory illusions conjured from the endless hiss of the universe by overly enthusiastic interpreters. The scientific rejection of these claims was swift and nearly universal. The core criticism focused on the complete lack of a physical mechanism. Space is a vacuum and sound waves cannot travel through it. While radio waves can travel through space, they are not sound. They are electromagnetic radiation. Converting them into sound is an arbitrary human translation for our convenience, not a revelation of some inherent audio property. For these sounds to be a genuine message, a civilization would have to intentionally modulate a radio carrier wave with a complex audio signal, a method vastly inferior to simply sending digital data for any purposeful communication. It would be an incredibly inefficient and bizarre way to transmit information across light years. Furthermore, the multi-step processing involved introduced so many opportunities for artifact and distortion that any faint, genuine signal would be utterly overwhelmed by the fingerprints of the processing itself, making the results scientifically unusable. Despite this overwhelming skepticism, the persistence of these claims reveals something profound about our relationship with the cosmos. They represent a deep, almost primal desire to hear a voice from the void, to receive a message not in the cold language of mathematics but in the warm, familiar form of sound and speech. It is a longing for a more intimate, less technologically mediated form of contact. These disputed detections, whether ultimately born of pareidolia or something else, highlight the immense challenge of searching for something when we cannot fully define what it is we are looking for. They serve as a cultural touchstone, a reminder that the boundary between rigorous science and hopeful speculation can sometimes become blurred when we stare into the infinite silence and desperately hope for something, anything, to call back in a voice we can recognize. Just as we train our most powerful telescopes on the depths of the cosmos, some of the most intriguing signals can come from startlingly close to home, reminding us that our own solar system still holds profound secrets. In a stunning turn of events, the key to one of these mysteries wasn't found by a mission designed to study planets, but by a probe on a daredevil mission to touch the Sun. NASA Parker Solar Probe has been repeatedly swinging by Venus, using the planet's gravity to fine-tune its orbit as it dives ever closer to our star. During these fleeting encounters, the probe's instruments are trained on the Sun, but in 2021, its sensitive antennas picked up something completely unexpected from the direction of Venus itself, a low-frequency radio signal emanating from the planet's atmosphere. This was far more than a simple blip. It was a robust, clear tone that should not, according to all our established models of Venus, have been possible to detect. The signal occurred at a frequency that places its origin within the ionosphere, the upper layer of the planet's atmosphere where gases are ionized by solar radiation. For decades, we've had a rough understanding of the density and composition of Venus's ionosphere, largely based on data from missions decades old. The Parker probe's detection, however, suggested a density far greater than anyone had predicted. The strength and clarity of the radio emission acted like a cosmic dipstick, measuring the ionosphere's electron density, and the reading was off the charts. It was as if we'd pointed a radar gun at a familiar local road and discovered a car traveling at 1,000 miles an hour. The finding defied the very physics we thought governed that environment. Scientists were immediately confronted with a puzzle. What could possibly cause such a dense and dynamic ionosphere on a world often described as a stagnant, hellish relic? The leading theory points to an 11-year cycle not of Venus but of our own Sun. We know the Sun's activity ebbs and flows in a predictable pattern, and the Parker probe's fly-by occurred during a period of remarkable solar quietness, a deep solar minimum. The new hypothesis suggests that during these extended periods of low solar activity, Venus's ionosphere may undergo a dramatic transformation, thinning out significantly more than we ever realized. Then, when the Sun's activity begins to ramp up again, the ionosphere could reform with a suddenness and intensity that creates these powerful, detectable radio emissions. We may have been lucky enough to catch the planet in a moment of atmospheric rebirth, a periodic event we've never before had the tools or the vantage point to witness. Of course, in any extraordinary discovery, the shadow of a more mundane explanation must be considered. The Parker Solar Probe is a technological marvel operating in an incredibly hostile environment, bombarded by radiation and intense heat. Could the signal be an artifact, a ghost in the machine created by the probe's own systems? This possibility was investigated with extreme rigor. The team analyzed the signal's behavior, its frequency, and the precise orientation of the spacecraft. The evidence was compellingly against an instrumental error. The signal changed predictably as the probe moved relative to Venus, and it matched the exact signature expected of a natural radio emission interacting with a planetary body. It pointed conclusively to a real phenomenon happening at Venus, not a glitch happening within Parker. This single, unexpected detection has done more than just add a new data point. It has fundamentally reignited scientific interest in our long-neglected planetary neighbor. For years, Venus was often dismissed as a burned-out case, a victim of a runaway greenhouse effect with little left to teach us. This signal loudly proclaims that assumption is false. It suggests that Venus is a far more dynamic and complex world than we imagined, with an atmosphere that may have its own rhythms and cycles intimately tied to the Sun's mood swings. It provides a thrilling new mystery for a forthcoming generation of Venus-bound missions, like NASA Da Vinci and Veritas and the European Space Agency's Envision, giving them a specific new question to answer. The Parker Solar Probe, in its quest to unravel the secrets of the Sun, has gifted planetary scientists a priceless clue, proving that sometimes the greatest discoveries are the ones you never even thought to look for. While the initial signal from the Sun-like star HD 164595 faded into frustrating silence, refusing to repeat for any of the world's most powerful telescopes, the story of this system was far from over. The intriguing radio detection acted like a starting pistol, prompting astronomers around the globe to turn a full battery of instruments toward this star 95 light-years away, examining it across every wavelength of light they could. What they began to uncover was a celestial portrait that was far more complex and dynamic than anyone had initially assumed, a system that seemed determined to keep its secrets by revealing deeper layers of mystery. One of the most compelling follow-up discoveries came not from radio dishes, but from the sharp infrared eyes of space telescopes. Detailed analysis of the star's emissions revealed a curious and significant infrared excess. This is a technical way of saying the star was emitting more heat in the infrared part of the spectrum than could be explained by the star itself. This excess energy is a classic signature of one thing, a circumstellar debris disk. Think of it as the celestial equivalent of a dusty attic, a vast ring or cloud of cold, fine dust and rocky debris. the leftover building blocks of planets that never formed or the shattered remains of asteroids and comets constantly colliding. The presence of this disk fundamentally changed the context of the system. It was no longer just a lone star with one known Neptune-sized planet. It was a mature, active planetary system with a history of violent construction, a place where the processes of planet formation might still be ongoing or where colossal collisions could be a regular occurrence. This discovery of abundant dust opened up a new and fascinating possibility for the initial radio signal. Could the strange transmission have been a natural, albeit extraordinarily powerful, phenomenon generated within this chaotic disk? Some researchers began to explore the idea of what they called a microlensing event. Here's how that might work. Imagine an immense rocky body, a planetesimal or a very large asteroid, within that debris disk suddenly experiencing a cataclysmic collision or a massive volcanic eruption. For a brief moment, that event could superheat the surrounding material, ionizing it and turning it into a temporary, natural lens for the star's own radio emissions. This turbulent, charged cloud could then focus and amplify the star's natural radio waves, shooting them out into the galaxy in a tight, intense beam that would, for all intents and purposes, look exactly like a powerful, narrowband artificial signal to anyone who happened to be in the path of that beam. It would be a cosmic bullhorn created by chance and powered by sheer celestial violence, a one-time natural amplifier that perfectly mimicked technology. Furthermore, the known architecture of the HD 164595 system adds another layer of plausibility to this idea. The single confirmed planet, HD 164595b, is a warm Neptune orbiting quite close to the star. But gravitational models strongly suggest that where there is one giant planet, there are often others further out. It is highly probable that this system contains additional, as yet undetected worlds orbiting within that very debris disk. The gravitational pull of these unseen planets would stir up the disk, perturbing the orbits of countless smaller bodies and dramatically increasing the frequency of high-energy collisions. The system could be a much more active and violent place than it appears from a distance, a perfect environment for generating the kind of singular, explosive event that could create a fleeting, brilliant radio burst. In this light, the initial signal begins to look less like a missed call from another civilization and more like a natural firework display in a busy and chaotic planetary construction zone. This shift in perspective doesn't make the signal any less significant. It simply places it within a new and equally thrilling scientific framework. The debate over HD 164595 has evolved from a simple binary question of alien or interference into a much richer discussion about the extreme and poorly understood phenomena that can occur in mature planetary systems. It challenges us to expand our catalogue of what natural astrophysics can produce. The system continues to be a prime target for observation, a laboratory for testing these new theories about natural radio amplifiers and the hidden dynamics of dusty disks. The star's greatest lesson may be that a negative result in the search for extraterrestrial intelligence is never truly a dead end. It is often the first step toward discovering something entirely new about the incredible physics of our universe. Sometimes the most profound discoveries in astronomy are born not from solemn analysis, but from a moment of shared, bewildered laughter among scientists staring at data that simply doesn't make sense. This is the story of a signal so bizarre that the astronomers who found it, half-jokingly, referred to it as LGM-2 Little Green Men 2. It began in 1989 as researchers sifting through data from the Parkes Radio Telescope in Australia stumbled upon a radio source that was both deeply familiar and utterly strange. It pulsed with the metronomic regularity of a pulsar, the spinning neutron star that serves as one of astronomy's most reliable clocks. But this clock was ever so slightly wrong. its rhythm marked by tiny, unpredictable hiccups and timing irregularities that defied the beautiful, precise mathematics governing every other pulsar known to science. The initial bewilderment was palpable. A pulsar's reliability is its defining feature. Its spin is so constant that the slowdown caused by energy loss can be measured over decades with incredible accuracy. This new object, however, seemed to have a mind of its own. Its pulses would arrive a fraction of a second early or late for no discernible reason, as if the cosmic timekeeper had developed a nervous twitch. In the context of the time, when the only known pulsing radio sources were pulsars, this bizarre behavior was deeply unsettling. The joke about little green men was a way to vent that scientific frustration, a tongue-in-cheek acknowledgement that this signal was so anomalous that an artificial origin felt for a fleeting moment almost as plausible as a natural one. It was a coping mechanism for confronting something that challenged the very categories they understood. The resolution to the mystery didn't come from a single eureka moment, but from patient observation and a theoretical leap. Astronomers eventually realized they weren't looking at a standard pulsar with a glitch. They were looking at an entirely new class of object. The source was indeed a rotating neutron star, but one with a profoundly powerful and complex magnetic field, orders of magnitude stronger than that of a typical pulsar. This object would come to be known as a magnetar. The strange timing irregularities weren't a sign of intelligence, they were the stellar equivalent of growing pains. The immense magnetic stress would warp the star's solid crust, causing sudden starquakes that would momentarily change its moment of inertia, making it spin ever so slightly faster or slower. They were listening to the sound of a celestial giant cracking under the pressure of its own immense power. The case of LGM-2 stands as a perfect historical echo of the challenges we still face today with signals like the repeating fast radio bursts. It illustrates the delicate, often humorous tightrope walk astronomers must perform when confronted with the truly unknown. The line between a new, violent natural phenomenon and a potential technosignature can be incredibly faint, discernible only through rigorous scrutiny and a willingness to let the data, not our hopes, guide the way. This signal, once a punchline about little green men, ultimately expanded our understanding of the neutron star family, teaching us that the universe is capable of creating engines of even greater ferocity and mystery than we had previously imagined. It was a powerful lesson in humility, a reminder that nature's imagination will always dwarf our own, and that the cosmos often saves its greatest wonders for those moments when we are willing to admit we have no idea what we're looking at. While the core of our galaxy has long been a known generator of cosmic weirdness, a signal detected in 2022 managed to stand out even against that chaotic backdrop, presenting a puzzle that has only grown more complex with time. Designated G0.4 plus 1.3, this transient radio source was first picked up by the Very Large Array in New Mexico and then confirmed by the Meerkat Array in South Africa. Unlike a fast radio burst that screams across the cosmos in milliseconds, this was a slower, more persistent event, a radio source that flickered to life, brightened significantly over several weeks, and then gradually faded away over months. But its most captivating feature wasn't its duration. It was its bizarre and unprecedented radio voice. The emission from this object exhibited a characteristic known as extreme frequency modulation, a quality that made it utterly unique. Imagine tuning an old analog radio and hearing a station that doesn't just play music, but whose very pitch bends and warps in a slow, hypnotic dance. That's what astronomers observed. The signal's brightness wasn't constant across all radio frequencies. It changed in a smooth, wave-like pattern, with the peak of its emission sweeping from higher frequencies to lower ones and back again over a regular cycle. This wasn't the random static of a stellar explosion or the steady pulse of a neutron star. It was a coherent, rhythmic phenomenon that suggested some kind of periodic physical process was governing its emission, a cosmic oscillator whose mechanism we couldn't identify. The immediate and most critical step in solving any astronomical mystery is to find a counterpart, to see the same object in visible light, X-rays or infrared, as each wavelength reveals a different piece of the puzzle. Teams around the world scrambled to point every available instrument at the coordinates, from the Chandra X-ray Observatory to the Hubble Space Telescope. The result was a profound and telling silence. There was nothing there. No star, no nebula, no remnant, no X-ray glow. The source was completely dark at every other wavelength of light, existing only as a ghost in the radio spectrum. This ruled out entire categories of objects. It wasn't a typical pulsar which would have been seen in X-rays. It wasn't a flaring star. It was an invisible engine pouring out energy in a very specific way that we had never witnessed before. So what could possibly lurk in the galactic center, emit powerful radio waves in a rhythmic frequency sweep, and yet remain completely invisible? Theorists have ventured into the realm of the exotic to find answers. One compelling idea involves a special class of dead star known as a magnetar. But this wouldn't be just any magnetar. It would need to be one orbiting the supermassive black hole Sagittarius, a star in a highly elliptical orbit. As it swung perilously close to the black hole on its nearest approach, the incredible tidal forces would flex and stress the neutron star's crust, potentially triggering massive starquakes and activating its immense magnetic field in a way that produces the observed radio modulation. The orbital period could then dictate the rhythmic cycle of the emission. Another, even more speculative theory posits the existence of a completely new type of celestial body, an exotic compact object. This could be something like a quark star or a prion star, theoretical entities even denser than neutron stars, where matter is broken down into its most fundamental subcomponents. The physics governing such an object would be wildly different from anything we currently understand, and its interaction with the unique environment of the galactic center, bathed in the intense gravitational field and particle winds from the central black hole, could produce radiative behaviors that are entirely novel to science. It would be a glimpse into states of matter that simply cannot exist anywhere else in the universe. The significance of the 2022 Galactic Center transient lies in its stubborn refusal to be categorized. It doesn't fit the profile of any known celestial source, and its unique location provides both a clue and a complication. The Galactic Center is an extreme environment, a laboratory of intense gravity, powerful magnetic fields, and high-energy particle collisions. This means it could be breeding grounds for phenomena that are exceptionally rare or short-lived, events we might only witness once in a generation of observing. This single, mysterious signal is a powerful reminder that even within our own galaxy, there are still fundamental discoveries to be made, and that the most familiar places can sometimes hide the most extraordinary secrets, waiting for just the right moment to reveal themselves. Imagine a signal that isn't really a signal at all, but rather a precise and deliberate absence, a carefully sculpted void in the constant cosmic static. This is the enigmatic story of the 2008 so-called dark radio signals, a series of detections that represent not what was heard, but what strangely and inexplicably wasn't. The discovery emerged from a meticulous analysis of data from the Parkes radio telescope, where astronomers weren't just looking for peaks of energy, they were employing sophisticated software filters designed to find the exact opposite. These algorithms were tuned to identify very specific, very brief moments of perfect radio silence, narrowband nulls in the data where the universe's background hiss suddenly dropped to zero for a fraction of a second before returning to normal. Finding such a perfect void is in many ways even more statistically shocking than finding a powerful burst, because the natural cosmos is almost never completely quiet. The statistical significance of these nulling events was what made them impossible to ignore. They weren't random blips, they appeared with a frequency and a signature that suggested an intelligent origin. The nulls were incredibly narrow in bandwidth, as if a cosmic finger had reached out and pressed the mute button on one specific radio station for a split second, leaving the channels on either side completely unaffected. This level of precision is virtually unheard of in nature, where radio emissions tend to be messy and broadband. It pointed towards a technology capable of not only broadcasting a signal, but of creating a perfectly shaped and precisely timed pocket of silence. The immediate and unsettling question was, why would anyone or anything do that? One compelling theory suggested it could be a form of ultra-secure communication. Imagine sending a message not by transmitting a pulse of energy, which can be easily detected, but by briefly removing a pulse of energy from a pre-arranged background source. To anyone else listening, it would just sound like a momentary drop in static, meaningless noise. But to a receiver that knew exactly which frequency to monitor and when to expect the null, it would be a clear binary digit, a one-bit message in a bottle made of silence. It would be the ultimate stealth communication, hiding information in plain sight by encoding it as a momentary nothing. This line of thinking inevitably leads to the most profound and controversial possibility, that these nulls are not a form of communication we understand, but evidence of an interaction with something entirely unknown, like dark matter. We know dark matter makes up about 85% of the matter in the universe, but we have no idea what it actually is. We can only observe its gravitational effects. Some physicists have proposed theoretical particles, like actions or other weakly interacting massive particles, that could theoretically clump together in strange ways. Perhaps these dense knots of dark matter could, under certain conditions, briefly absorb or scatter radio waves of a very specific frequency, creating a temporary shadow in the radio spectrum as they pass between us and a distant background source. This would make the dark radio signals not a message, but a footprint, the first ever indirect detection of the invisible scaffolding of the cosmos, revealed only by the silent shadow it casts as it moves through the universe. Of course, the scientific community remains deeply divided. Skeptics argue quite persuasively that the most likely explanation is still an ultra-rare and poorly understood form of terrestrial interference. Our planet is enveloped in a thickening fog of radio noise from satellites, radar, and countless other technologies. It is entirely possible that a complex interplay of signals, perhaps from a secret military source using sophisticated frequency hopping techniques, could create a brief, perfect null in the data that mimics a celestial origin. The fact that these events have been so difficult to replicate lends weight to this argument, yet the sheer elegance of the signature, its statistical improbability, and its resistance to any easy classification have cemented the dark radio signals as one of the most perplexing and philosophically challenging anomalies in the modern era. They force us to confront the limits of our knowledge, asking us to consider not only what strange messages might be hidden in the noise of the universe, but what profound secrets might be waiting for us in the silence. Of all the stars in our night sky, few are as iconic or as foreboding as Betelgeuse, the fiery red shoulder of the constellation Orion. A massive red supergiant, it's a star living on borrowed time, destined to end its life in a spectacular supernova explosion that will be visible from Earth even in broad daylight. So in late 2019, when astronomers around the world noticed the star beginning to dim dramatically, a palpable sense of excitement rippled through the community. This was it, many whispered, the great dimming had begun. Was this the final act, the prelude to a cosmic detonation that would rewrite the night sky? As telescopes of every kind swiveled to watch, a fascinating and unexpected subplot emerged, not in the familiar realm of visible light, but in the silent whispers of radio waves. While the world watched the star's visual brightness plummet by over 35%, a team using the immense Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile, was tracking Betelgeuse's emissions at much longer wavelengths. What they found was completely counterintuitive. As the star grew dramatically darker to our eyes, its brightness in the radio part of the spectrum actually increased. This was the exact opposite of what a simple model would predict. If the dimming were caused by something straightforward, like the star simply cooling down, then its radio brightness should have decreased in lockstep with its optical light. The fact that it did the opposite was a clear signal that something far more complex and interesting was happening on and around Betelgeuse. The radio waves were telling a different story than the optical light, and decoding that story became an urgent astronomical puzzle. Theorists quickly assembled a suite of possible explanations, each one painting a picture of a star in the throes of immense internal turmoil. The leading hypothesis involved a colossal outburst of stellar activity. Imagine a titanic convection cell, a bubble of plasma larger than the orbit of Jupiter, boiling up from Betelgeuse's ferociously hot interior and erupting onto its surface. This eruption would have hurled an enormous amount of material out into space, not as a smooth shell, but as a vast, localized cloud of relatively cool, dusty gas. From our distant vantage point, if that cloud happened to drift directly across our line of sight, it would act like a cosmic sunshade, selectively blocking the visible light from the star's photosphere and causing the dramatic dimming we observed. However, this same cloud of material would be a very different environment for radio waves. The cool dust grains within the cloud would themselves be efficient emitters of radio waves, effectively making the entire cloud glow brightly at those longer wavelengths. So, while the cloud was hiding the star's visible face, it was simultaneously putting on a radio show, perfectly explaining the observed inverse relationship. An alternative and equally compelling theory looked not to a single eruption, but to a routine yet profound change in the star's own atmosphere. Red supergiants like Betelgeuse are notoriously unstable, constantly pulsating and shedding their outer layers in a steady stellar wind. The radio brightness of a star is intimately tied to the density and temperature of its chromosphere, the complex layer of atmosphere just above its visible surface. It's possible that during the Great Dimming, a particularly large and cool convective cell reached the surface, causing a temporary but significant cooling of the star's chromosphere. A cooler chromosphere would actually become more transparent at radio frequencies, allowing us to see deeper into the star, into hotter and brighter layers that are normally hidden from view. In this scenario, we weren't seeing the glow of a dust cloud, but were instead granted a rare, deeper X-ray vision of the star's inner workings, all because its outer atmosphere had momentarily shifted and cleared a path. The resolution to the mystery came from a powerful combination of observations. By the time Betelgeuse returned to its normal brightness in 2020, the evidence had overwhelmingly coalesced around the dust cloud theory. Spectroscopic data had confirmed the presence of specific molecules in the light that are associated with cool gas, and high-resolution images from instruments like the Very Large Telescope even managed to glimpse patches of cooler material on the star's southern hemisphere. The Great Dimming was not a sign of an imminent supernova. It was a spectacular but routine episode of stellar weather on a truly monstrous scale. The radio signals were the key that unlocked this truth. They provided a critical piece of evidence that visible light alone could not, demonstrating that the star itself was fundamentally unchanged, merely temporarily obscured by its own exhalations. This event transformed our understanding of red supergiants, revealing them not as placid, fading embers, but as dynamic, violent, and unpredictable beasts, capable of reshaping their own immediate environment in ways we are only beginning to comprehend. While we've been listening to the cosmos, training our most powerful radio telescopes on the void in hopes of hearing a whisper, an entirely different kind of signal has been captured not by ears, but by eyes, the most sophisticated eyes we've ever placed beyond our atmosphere. The James Webb Space Telescope was designed to be a time machine, to peer back into the dawn of the first galaxies and see them with a clarity never before possible. It has succeeded beyond our wildest dreams, but in doing so, it has also opened a Pandora's box of new mysteries, revealing unexpected patterns in the infrared light of the ancient universe that challenge our very understanding of cosmic evolution. These aren't radio bursts or pulse transmissions. They are silent, spectral anomalies written in the heat of the most distant objects we can see. One of the most startling discoveries involves the very first galaxies JWST observed. According to our most robust cosmological models, the early universe should have been a place of gradual assembly. The first stars and galaxies were predicted to be relatively small and simple, slowly merging over billions of years to form the grand spirals and ellipticals we see today. But JWST found the opposite. The data reveals galaxies that are not only shockingly massive and bright, but also appear to be incredibly mature, with structures like disks and bulges that should have taken much longer to form. The infrared light from these ancient giants tells a story of a universe that got busy far faster than any simulation predicted, as if the rules of physics as we know them were operating on a different timescale in the early cosmos. It's a signal not of sound, but of scale and structure, and it has sent cosmologists back to the drawing board. The infrared anomalies extend beyond just size and shape. The spectra of these distant galaxies, the detailed fingerprint of their light split into its constituent wavelengths, contain puzzling features. Astronomers are detecting unexpected dips and peaks in the infrared signatures, suggesting the presence of certain elements and molecules in abundances that defy explanation. Some galaxies show signs of oxygen and neon far earlier than should be possible, elements forged in the hearts of massive stars and scattered by their supernova deaths. This implies a period of frantic, explosive star formation and death, a starburst on a cosmic scale that seems to have enriched the entire galaxy with heavy elements in a cosmic blink of an eye. Other spectral lines remain unidentified altogether, hinting at chemical processes or states of matter we have not yet catalogued, a silent testament to the unknown physics at work in the universe's nursery. Faced with this barrage of unexpected data, the scientific community has split into several camps, each proposing a different solution to the puzzle. One group suggests our understanding of star formation itself is incomplete. Perhaps in the denser, purer environment of the early universe, the first stars formed with vastly different properties. So-called population Roman III stars, behemoths that lived fast, died young, and seeded their galaxies with elements with an efficiency we don't see today. Another, more radical theory involves alternative dark matter models. Maybe the mysterious substance that makes up most of the universe's mass isn't cold and slow-moving as in the standard model, but is slightly warm, allowing it to clump together on smaller scales earlier in time, providing the gravitational scaffolding for galaxies to form at a breathtaking pace. And then there is the humbling, ever-present possibility that the anomalies are not in the stars, but in our instruments. The James Webb Space Telescope is a masterpiece of engineering, but it is also an incredibly complex machine observing in wavelengths we have never explored with this level of sensitivity. Could subtle, uncalibrated instrumental effects or our incomplete models of its own performance be introducing artifacts that look like cosmic mysteries? Teams are tirelessly working to rule this out, but it serves as a crucial reminder that when you open a new window on the universe, the first things you see might include the faint reflections from the glass itself. The ultimate lesson from JWST anomalous signals is one of profound humility. We built the most advanced observatory in history to find answers, and it has instead given us better, sharper, more detailed questions. It has revealed that the infant universe was not a simpler place, but a more dynamic and extreme one, operating under a set of rules we are only beginning to glimpse. Each new image, each new spectrum, is not a conclusion but a starting point, a signal from the depths of time reminding us that every answer unravels a deeper layer of mystery, and that the cosmos will always have secrets waiting just beyond the reach of our latest and greatest machines. While the search for deep space mysteries captivated the public, another enigma was unfolding much closer to home, not in the profound silence between galaxies, but in the increasingly crowded orbital space around our own planet. The story begins not with a formal scientific announcement, but with the diligent efforts of a global network of amateur radio operators, enthusiasts who scan the skies with home-built equipment, listening to the constant chatter of satellites as they circle the Earth. In the early 1990s, a number of these highly skilled listeners began reporting something strange. They were detecting transmissions from orbital objects that weren't supposed to be there, broadcasting on frequencies that didn't match any known civilian or commercial satellite. These weren't the structured data streams of weather satellites or the familiar beacons of scientific probes. These signals were different, often characterized by unusual modulation patterns, complex, pulsed, or frequency-hopping transmissions that seemed designed to avoid easy interception or decoding. The most compelling accounts centered on a specific type of signal detected around 1993. Operators reported picking up incredibly strong, narrowband transmissions on frequencies typically reserved for military use, often in the UHF and SHF bands. The modulation was sometimes described as squealing or harsh, a far cry from the clean, predictable signals of scientific missions. The behavior of these phantom satellites was just as mysterious as their voices. They would appear without warning, broadcast for a variable period, sometimes hours, sometimes days, and then vanish from the spectrum just as suddenly as they had arrived. Their orbits, when they could be roughly triangulated by operators in different parts of the world, often seemed to be highly elliptical or even geosynchronous, a hallmark of sophisticated intelligence gathering or communications platforms. The natural and immediate assumption was that these were clandestine military satellites, so-called black satellites, launched in total secrecy by world superpowers to conduct covert operations away from the prying eyes of the public and their geopolitical rivals. This explanation, while perfectly logical, quickly ran into its own set of puzzling complications. The end of the Cold War and the subsequent gradual declassification of many space projects revealed a great deal about previously secret military satellite fleets. While many of the mysterious signals were indeed accounted for by these admissions, a stubborn handful of detections from the early 90s refused to be neatly filed away. Some of the reported orbits were physically implausible for known satellite technology of the era, requiring maneuvers that would have consumed impossible amounts of fuel. Even more perplexing were signals that exhibited a phenomenon operators called ghosting, where a transmission would be heard from two slightly different orbital positions almost simultaneously, as if one object was shadowing another, or as if a single satellite was projecting a false radar signature through electronic means. The most anomalous reports described signals that would change their modulation and frequency mid-transmission in a complex, non-repeating pattern, a feat of software-defined radio that was years ahead of its time. This has created a lasting legacy of ambiguity. The realm of unidentified satellite signals remains a fascinating gray area where hard data is scarce and informed speculation is plentiful. It represents a perfect storm of factors: the undeniable existence of highly classified space missions, the incredible skill and credibility of the amateur satellite tracking community, and the inherent difficulty of pinpointing the exact source and nature of a radio emission from the ground. For every mysterious signal that can be dismissed as a misinterpreted piece of space debris or a secret military test, there remains a core of detections that continue to intrigue researchers. They serve as a reminder that even in the space immediately surrounding our world, there are still pockets of mystery, activities conducted in silence and secrecy that occasionally leak out onto the public airwaves, offering a fleeting, cryptic glimpse into the hidden world of orbital operations and leaving us to wonder just how much of what's flying over our heads remains official. Unacknowledged. From the legendary one-time shout of the wow signal to the metronomic precision of the repeating fast radio bursts, the sheer variety of these cosmic enigmas is what makes this search so endlessly captivating. We've journeyed through whispers from our nearest stellar neighbor and colossal blasts from galaxies billions of light years away, each one a unique fingerprint that refuses to match any in our existing celestial database. Some signals, like the rhythmic pulse from a globular cluster or the strange frequency sweep from the galactic center, point toward bizarre new classes of celestial objects, neutron stars behaving in ways we never predicted, or perhaps something even more exotic that we haven't yet dreamed of. Others, with their perfect narrowband focus on the universal hydrogen line, tease us with the possibility of a different kind of origin, one that speaks not to the chaotic laws of physics, but to the deliberate action of intelligence. This is the great and humbling frontier of modern astronomy, a universe that is not silent, but is instead filled with a chorus of voices we are only just learning to hear and, more importantly, to understand. What binds all these mysteries together is their power to push the boundaries of science itself. Each unexplained signal is not a dead end. It is a signpost pointing toward a gap in our knowledge, a challenge to our existing models of how the cosmos works. The frantic theorizing that follows every new discovery, the magnetar starquakes, the colliding asteroids, the binary interactions, and even the speculative megastructures, is not scientists guessing wildly. It is the vital, exhilarating process of science at work, of imagination being forced to confront evidence and expand. These signals are the universe's way of asking us questions, and in our struggle to answer them, we are compelled to build better telescopes, develop sharper algorithms, and ultimately see the cosmos with new eyes. They remind us that for all we have learned, we are still beginners in a grand and ancient conversation. So as we look up at the night sky, let's not see it as a static painting, but as a dynamic, living puzzle. The story of these signals is still being written, and with every new observation we add another line. We want to know what you think. Which of these 30 signals captured your imagination the most? Was it the tantalizing, one-time mystery of the wow signal, the clockwork perfection of a repeating FRB, or the strange spectral anomalies from the James Webb Space Telescope? Share your favorite theory in the comments below. Do you believe the answer to one of these puzzles lies in known physics pushed to its extreme? Or are we on the cusp of discovering something that will fundamentally reshape our place in the universe? The greatest lesson from all of this is that the cosmos is far stranger and more wonderful than we could ever imagine. And the next great discovery is always just one signal away, waiting for the right moment to break through the static and change everything we think we know.